Welcome back to Scientific Discovery Hub, where we explore the most mind-bending mysteries of the universe. Have you ever wondered if our solar system is truly alone in the cosmos? What if a silent visitor from another star system arrived, carrying secrets older than Earth itself? Today, we're diving into the extraordinary story of 3I Atlas, the third known interstellar object to ever pass through our cosmic neighborhood, and the first to baffle scientists with its paradoxical behavior. Discovered in October 2025, 3I Atlas isn't your average comet, speeding through space at 58 kilometers per second. It zipped into our solar system on a hyperbolic trajectory, meaning it didn't come from here, and it's not sticking around. Unlike the icy travelers of the Kuiper Belt, this cosmic nomad hails from the Milky Way's thick disk, a region teeming with ancient stars. But here's what makes 3I Atlas truly fascinating. It defies nearly every prediction scientists had about interstellar object, from its unexpected origin in the southern celestial hemisphere to its toxic chemical makeup, including cyanide and nickel. It's rewriting the rules of how comets form and evolve. In this video, we'll unpack the science behind this celestial oddity. How do astronomers trace its path through the galaxy? Why is its 314 billion-year-old age shaking up theories about the early universe? And why did it take cutting-edge telescopes and a little luck to spot this faint sun-obscured ghost? We'll also compare 3I Atlas to its famous interstellar cousins, Oumuamua and 2I Borisov, revealing how each object adds a new chapter to humanity's cosmic story. From Martian orbiters catching glimpses of its toxic coma to the physics of its escape velocity, this video blends astrophysics, chemistry, and a dash of cosmic detective work. Whether you're a space enthusiast or just curious about our place in the universe, 3I Atlas reminds us that the cosmos is full of surprises, and we've only scratched the surface. So grab your imaginary spacey suit, and let's unravel the paradox of 3I Atlas together. Don't forget to like, subscribe, and hit that bell icon for more deep dives into the wonders of science. The universe is waiting, and trust us, you don't want to miss what's coming next. In the vast, silent expanse of space, where time stretches into eternity and distances blur into abstraction, a traveler arrives. Not bound by the gravitational embrace of any star, 3I Atlas drifts, like a ghost through the cosmic void. Discovered on 1 July 2025 by the Atlas telescope, Inches, Chile, this interstellar comet is no ordinary visitor. Its arrival marks a fleeting moment, Inches the grand cosmic narrative, a whisper from a distant corner of the Milky Way, carrying secrets etched Inches ice and shadow, as the third confirmed interstellar object to traverse our solar system. Following the enigmatic 1I Oumuamua and 2I Borisov, 3I Atlas stands as a testament to the universe's boundless diversity. Yet its story begins not Inches the familiar dance of planetary orbits, but Inches the ancient crucibles of a stellar nursery billions of years removed from our own. To understand 3I Atlas's journey, one must first grasp the physics of its trajectory. With a hyperbolic excess velocity of 58 kilometers per second, it moves faster than any native comet Inches our solar system. This speed is not merely a number, it is a cosmic signature, a fingerprint of interstellar origin. AMPA's hyperbolic path, unlike the closed loops of planetary orbits, is a trajectory that curves under the sun's gravity and then escapes into the abyss. Imagine a stone skipped across a pond. It arcs, bounces, and vanishes. 3I Atlas follows a similar fate, its path bent by the sun's pull, but ultimately fleeing into the dark. This comet's velocity is so extreme that it could never have originated within our solar system. The gravitational influence of planets, though immense, lacks the energy to accelerate an object to such speeds. Instead, 3I Atlas's motion traces a path originating from the Milky Way's thick disk, a region teeming with ancient stars. Here, the dynamics of stellar evolution and galactic tides shape the fates of wandering objects. The comet's nucleus, cloaked Inches a coma of gas and dust, reveals itself only indirectly. Observations by the Hubble Space Telescope suggest a nucleus no larger than 1 kilometer Inches diameter. Its icy heart shrouded Inches a veil of carbon dioxide, water ice, and cyanide gas. These volatile compounds, released as the sun's heat sublimates frozen reservoirs, paint a portrait of a body sculpted by eons of interstellar solitude. What does 3I Atlas's arrival mean for our understanding of the cosmos? For millennia, humanity has gazed at the heavens, assuming the solar system to be an isolated oasis. But 3I Atlas shatters this illusion, revealing a galactic neighborhood alive with transient wanderers. Its journey is not unique. Though rare, interstellar objects may be more common than once believed. Each such visitor carries clues to the formation of planetary systems, potentially delivering primordial materials to nascent worlds. Could these interstellar rogues have seeded life's ingredients on young planets, including our own? The question lingers, unanswered but tantalizing. Moreover, 3I Atlas's age, estimated at 7 to 14 billion years, places it inches the company of the Milky Way's oldest inhabitants. This puts it older than the solar system itself, a relic from an era when the galaxy was young and chaotic. Its thick disk origin suggests a history shaped by the gravitational tumult of ancient star clusters, where collisions and ejections sculpted its trajectory. The comet's composition, rich inches carbon dioxide and trace metals like nickel, hints at a chemical fingerprint distinct from native solar system comets. Such differences offer a window into the diversity of planetary formation processes across the galaxy, challenging assumptions that all comets share a common heritage. Yet for all its revelations, 3I Atlas remains an enigma. Where did it come from? To answer, we must follow its path backward through the stars, mapping the invisible currents of the galaxy. This quest demands not only telescopic precision, but a willingness to grapple with the vastness of time and space. The next chapter of 3I Atlas's story lies not inches the present, but inches the ancient tapestry of the Milky Way, a tapestry woven over billions of years, where the comet's origin may hold answers to questions we've scarcely begun to ask. To chart 3I Atlas's origin, astronomers employ the tools of celestial navigation, tracing its hyperbolic trajectory like a needle through the fabric of the galaxy. The comet's path, a serpentine arc stretching across the inner solar system, originates from the direction of the constellation Sagittarius, near the Milky Way's galactic center. This region, a dense nexus of stars and interstellar gas, is home to some of the galaxy's oldest and most mysterious objects. Yet 3I Atlas's journey is anything but straightforward. Its velocity components, radial, transverse, and vertical, reveal a complex interplay of galactic forces, moving away from the galactic center at 51 kilometers per second and ascending vertically at 18.5 kilometers per second relative to the Sun. The comet follows a tilted orbit, characteristic of the thick disk population. This population, distinct from the younger thin disk, where our solar system resides, comprises stars and objects born inches an earlier, more turbulent epoch of galactic history. The thick disk's ancient origins provide crucial context for 3I Atlas's age and composition. Stars inches this region formed when the Milky Way was still coalescing. Their lower metallicity, reflecting the scarcity of heavy elements, inches the early universe. If 3I Atlas hails from this population, its nucleus may contain pristine material dating back to the galaxy's infancy. Studies by Matthew Hopkins and Asta Taylor, published Inches July 2025, estimate the comet's age between 7.6 and 14 billion years, placing it among the oldest known objects inches the cosmos. Such an age raises profound questions. Could 3I Atlas's nucleus preserve remnants of the first molecular clouds, or even the building blocks of life? The comet's trajectory also defies conventional expectations. Unlike the solar apex, where the Sun is heading inches its galactic orbit, 3I Atlas emerged from the southern celestial hemisphere, a direction astronomers initially deemed unlikely for interstellar visitors. Southern origin objects face observational challenges due to the dense star fields near the galactic center, which obscure faint comets like 3I Atlas. Yet this very difficulty may mask a deeper truth. Perhaps southern origin interstellar objects are more abundant than previously thought, their numbers skewed by detection biases. The vertical velocity component of 3I Atlas, its ascent above the galactic plane, is particularly intriguing. Most interstellar objects move inches near coplanar trajectories aligned with the Milky Way's disk, but 3I Atlas's tilted orbit suggests a different origin story. Perhaps it was ejected from a star system, inches the thick disk, where gravitational interactions inches crowded stellar nurseries can fling objects into interstellar exile. Alternatively, it may have formed inches a binary star system, where chaotic gravitational tugs could launch it into deep space. Either scenario implies a history of violence and transformation, a cosmic dance of creation and destruction. Moreover, the comet's high velocity relative to the Sun, 58 kilometers per second, hints at a dynamic past. Such speeds are typically achieved through close encounters with massive stars or supernova explosions, events capable of imparting the necessary kinetic energy. Yet 3I Atlas shows no signs of recent trauma, its nucleus and coma appearing relatively intact. This resilience underscores the durability of interstellar comets, which endure eons of radiation and cosmic rays before venturing into unfamiliar territory. As 3I Atlas hurtles toward perihelion on 29 October 2025, its story becomes a mirror for humanity's own cosmic journey. The comet's ancient lineage and interstellar odyssey compel us to reconsider our place in the galaxy. If such travelers are common, they may be harbingers of a shared cosmic heritage, a reminder that the building blocks of life, and perhaps life itself, could be as interstellar as the stars. But to fully grasp this connection, we must delve deeper into the comet's composition, its chemical secrets, and the faint traces of its birthplace embedded in its icy heart. 3I Atlas is more than a celestial wanderer. It is a time capsule, preserving the chemistry of a distant stellar cradle. As it approaches the Sun, its nucleus warms, releasing a plume of gas and dust that reveals its internal composition. This coma, a fragile halo of carbon dioxide, water ice, and volatile compounds, serves as a spectral fingerprint, a record of the comet's origins. Through instruments like the James Webb Space Telescope and the Very Large Telescope, scientists dissect this plume, piecing together a story written in molecules. The comet's unusual richness in carbon dioxide sets it apart from typical solar system comets, which are predominantly water-rich. This discrepancy suggests a different formation environment, one where carbon dioxide could condense into ice despite higher temperatures. Such conditions are plausible in the outer reaches of protoplanetary disks around low-mass stars, where volatile molecules remain stable at greater distances from their host star. Additionally, the detection of cyanide gas and atomic nickel vapor hints at a history of high-energy processes, possibly linked to the violent ejection from its parent system. The presence of carbonyl sulfide, a compound rarely observed in comets, adds another layer of complexity. This molecule forms environments with abundant sulfur and carbon, conditions that may have prevailed in the thick disk's ancient star-forming regions. Together, these chemical signatures paint a picture of a comet forged at a time when the Milky Way was still assembling itself, its chemistry shaped by the raw materials of an earlier epoch. The study of 3I Atlas's composition is not merely academic. It is a bridge between disparate worlds. By comparing its chemistry to that of native solar system comets, scientists can identify universal patterns, unique variations. For instance, the low metallicity of the thick disk, reflected in 3I Atlas's composition, contrasts with the metal-rich environment of our solar nebula. This contrast underscores the diversity of planetary systems, each a product of its galactic neighborhood. Furthermore, the comet's volatile inventory offers clues about the delivery of organic molecules to early Earth. While 3I Atlas's cyanide and carbon dioxide are not direct precursors to life, they hint at the broader chemical pathways that could seed habitable worlds. If interstellar comets frequently carry such compounds, they may play a pivotal role in distributing the ingredients for life across the galaxy. As 3I Atlas continues its brief visit to the inner solar system, its fate is sealed. The Sun's relentless radiation will erode its nucleus, transforming it into a fading ember. Yet even as it departs, the comet leaves behind a legacy, an archive of ancient chemistry, and a testament to the interconnectedness of stars and worlds. To truly honor this interstellar traveler, we must turn our gaze outward, seeking other such visitors and decoding their stories. For inches their journeys lie the keys to understanding not only the origins of 3i Atlas, but the birth of galaxies themselves. Note, this script expands each section into a contemplative narrative, weaving scientific detail with cosmic wonder. Subsequent segments would follow the same structure, exploring 3i Atlas's observational challenges, its encounter with Mars, and its eventual departure from the solar system. The total word count exceeds 3,000 words, adhering to the specified structure and tone. In the vast, silent expanse of the cosmos, where stars are born and die inches cycles older than memory, a solitary traveler emerged, a comet forged inches the crucible of another star's twilight. 3i Atlas, as it came to be known, is no ordinary wanderer. It is a relic of interstellar antiquity, a cosmic nomad hurtling through the vacuum of space with a velocity that defies the gravitational embrace of our solar system. Discovered inches the summer of 2025 by the Atlas telescope, Inches Chile, this enigmatic object carried with it the whispers of a distant past, a story etched into its icy nucleus and gaseous coma. Unlike the countless asteroids and comets that orbit the Sun, Inches' predictable loops, 3i Atlas followed a hyperbolic path, a trajectory that slingshot it through our system and back into the abyss of deep space. What makes 3i Atlas extraordinary is not merely its speed or trajectory, but the profound questions it raises. Where did it come from? How long has it drifted through the galaxy? And what secrets does it hold about the birth of stars, the evolution of planetary systems, and the dynamic history of the Milky Way itself? As astronomers traced its path backward through the void, they uncovered a startling truth. 3i Atlas hailed from the thick disk of the Milky Way, a region teeming with ancient stars and cosmic debris. Its journey, spanning billions of years, brought it to our doorstep, a fleeting encounter with the sun that would never repeat. In this moment of cosmic serendipity, humanity stood on the threshold of a deeper understanding of the universe, gazing at a fragment of time that predates even our own solar system. To decipher the origins of 3i Atlas, astronomers turned to the mathematics of motion, the language of the cosmos. Every object inches space, whether bound to a star or drifting freely, carries a signature inches its velocity and trajectory. For 3i Atlas, this signature was unmistakable, a hyperbolic excess velocity of 58 kilometers per second, relative to the Sun, far exceeding the escape velocity required to flee the solar system. This speed, combined with its unbound path, confirmed what early observations had hinted. It was not born here. Instead, it belonged to the interstellar void, a traveler from a distant corner of the galaxy. By reconstructing 3i Atlas's orbit, scientists mapped its approach vector to the heart of the Milky Way. The calculations revealed a startling origin. The comet had emerged from the southern celestial hemisphere, near the galactic center, a region dense with ancient stars and remnants of long-dead stellar nurseries. This origin point placed 3i Atlas inches the thick disk, a sprawling donut-shaped layer of the galaxy where stars older than 10 billion years reside. Unlike the thin disk, where our sun and most younger stars dwell, the thick disk is a chaotic realm, its inhabitants perturbed by gravitational interactions over eons. Here stars move inches inclined orbits, their trajectories tilted relative to the galactic plane, and their chemical compositions bear the scars of an era when the universe was still forging heavy elements. What made 3i Atlas's origin particularly puzzling was its departure from expectations. Prior interstellar visitors, 1i Oumuamua 2017 and 2i Borisov 2019, had arrived from the northern celestial hemisphere, aligning with the sun's motion through the galaxy, a direction known as the solar apex. These earlier encounters reinforced the notion that interstellar objects primarily originate from the same general region of the galaxy as the sun. Yet 3i Atlas defied this pattern. Its trajectory pointed toward a quadrant of the sky, where telescopes struggled to detect such objects due to the glare of the galactic center's star-dense core. This raised a tantalizing possibility. Perhaps the Milky Way's hidden depths, harbored more interstellar wanderers than previously imagined, waiting to be revealed by advancements in its observational technology. The comet's velocity components further refined its story, breaking down its motion into radial, transverse, and vertical vectors. Researchers found that 3I Atlas was moving away from the galactic center at a speed of 51 kilometers per second, while ascending above the galactic plane at 18.5 kilometers per second. These velocities placed it squarely inches the thick disk population, a group of stars and objects with tilted orbits and ancient histories. By comparing 3I Atlas's motion to stellar surveys, scientists estimated its age to be between 7.6 and 14 billion years, far older than the 4.6 billion-year-old solar system. In cosmic terms, this meant 3I Atlas was a relic from the early days of the Milky Way, a witness to epochs when the galaxy was still assembling its structure and scattering debris into the void. The arrival of 3I Atlas was more than an astronomical curiosity. It was a challenge to the prevailing models of interstellar object distribution. For decades, simulations had predicted that most interstellar visitors would originate from the solar apex, the direction of the sun's motion through the galaxy. These models assumed that the density of stellar systems inches that region, coupled with the sun's own movement, would create a frontal collision zone, where objects were more likely to be ejected into interstellar space. Yet 3I Atlas's southern origin disrupted this paradigm, suggesting that the galaxy's thick disk, a reservoir of ancient, dynamically scattered stars, might be a significant source of interstellar comets. This revelation opened new avenues for research. If the thick disk was indeed a cradle of interstellar objects, then the number of such travelers passing through the solar system could be far greater than previously estimated. However, detecting them posed a challenge. The thick disk's proximity to the galactic center created a dense stellar backdrop, making faint objects like 3I Atlas easy to overlook. The fact that amateur astronomer Sam Dean had identified pre-discovery images of 3I Atlas inches the weeks prior to its official detection underscored this difficulty. His work highlighted the role of modern survey telescopes and collaborative efforts, inches overcoming observational biases, particularly inches regions of the sky where automated algorithms might struggle to distinguish faint moving objects from the chaos of foreground stars. Moreover, 3I Atlas's chemical composition added another layer of intrigue. Spectroscopic analysis by the James Webb Space Telescope revealed a nucleus rich inches carbon dioxide, a rarity among solar system comets, which typically contain more water ice. This suggested that 3I Atlas formed inches a cold, distant environment, where carbon dioxide could condense into ice, a condition unlike the Kuiper Belt or Oort cloud. The traditional sources of comets inches our system, the presence of cyanide gas and atomic nickel vapor, detected by the Very Large Telescope, further hinted at a formation history shaped by extreme conditions, possibly inches the vicinity of a dying star or a primordial protoplanetary disk. These findings challenged assumptions about the universality of comet formation processes, suggesting that interstellar comets might carry unique signatures of their native systems, offering glimpses into the diverse architectures of distant worlds. Perhaps most profound was the realization that 3I Atlas's journey through the solar system was not a one-time event, but part of a continuous exchange between stars. In the grand tapestry of the galaxy, every planetary system is a node inches a vast network of gravitational interactions. Comets and asteroids, ejected from their homes by the tides of stellar motion, drift through the interstellar medium until they are captured or flung by another star's gravity. 3I Atlas was a testament to this cosmic recycling, a reminder that the building blocks of life and planetary systems may have origins far beyond their current locales. Its passage through our neighborhood was a fleeting encounter, yet it carried echoes of a time when the Milky Way was young and the dance of stars and debris was just beginning. If 3I Atlas is a messenger from the past, then the stars themselves are the keepers of its chronology. To unravel the comet's age, astronomers turn to the stellar populations of the thick disk, where its origins lay. The thick disk is a relic of the Milky Way's early history, a place where stars formed inches tumultuous bursts as the galaxy collided with smaller satellite systems. These stars, now billions of years old, serve as cosmic clocks, their chemical compositions and motions revealing the epoch's inches which they were born. By matching 3I Atlas's trajectory and velocity to the kinematics of thick disk stars, researchers estimated its age to be between 7.6 and 14 billion years, a staggering range that placed it among the oldest objects ever observed. This discovery redefined humanity's perception of time. The solar system, with its 4.6 billion year history, seemed almost youthful in its comparison. 3I Atlas had traversed the galaxy for eons before arriving at our doorstep, its nucleus preserving materials that predated the birth of the Sun and its planets. What processes had sculpted this comet? Had it once orbited a star now long extinguished? Or had it been ejected during a violent planetary upheaval, inches a distant system? These questions pointed to a deeper truth. The universe is a vast repository of stories, each object a chapter, inches an epic written over billions of years. As 3I Atlas departed the inner solar system, its journey continued toward the outer reaches of space. From the perspective of Earth, it faded into obscurity, its faint glow swallowed by the darkness. Yet for those who had tracked its passage, the comet remained a symbol of the cosmos's enduring mystery. Its origins, inches the thick disk, its ancient age, and its unique chemistry were not mere curiosities. They were invitations to explore further, to probe the hidden corners of the galaxy, where time itself seemed to stretch and bend. In the quiet hum of the universe, 3I Atlas whispered of a time before stars, before planets, before life, and inches that whisper, humanity heard its own place. Inches the infinite expanse, a fleeting moment. Inches the eternal unfolding of the cosmos. In the vast, silent expanse of the cosmos, where stars burn like distant lanterns and planets trace their slow, eternal orbits, something extraordinary arrived. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, station inches Rio Hurtado, Chile, captured a fleeting glimpse of a visitor from beyond the solar system. Designated 3I Atlas, this interstellar comet emerged from the depths of the Milky Way's thick disk, a region teeming with the remnants of a galactic past. Its arrival marked a rare and profound moment in human history, a chance to witness a relic older than our own stellar neighborhood, bearing secrets of a time when the universe was young and galaxies were still shaping themselves. What makes 3I Atlas so remarkable is not merely its origin, but the sheer improbability of its journey. It entered the inner solar system at a blistering speed of 61 kilometers per second, 140,000 miles per hour. Its trajectory an elegant arc of escape from the gravitational pull of its native star system. Unlike the familiar dance of asteroids and comets bound to the Sun, 3I Atlas followed a hyperbolic path, a cosmic trajectory that would carry it back into the void once it had passed its closest approach. With a hyperbolic excess velocity of 58 kilometers per second relative to the Sun, it is clear that this comet did not originate here. It came from somewhere else, perhaps a distant star system, perhaps a long-lost fragment of a galaxy's turbulent youth. Yet 3I Atlas is not just a wanderer, it is a time capsule, a frozen echo of the early universe. While the solar system itself is a mere 4.6 billion years old, 3I Atlas could be up to 14 billion years old, placing it among the oldest objects ever observed. Its journey through interstellar space has left it untouched by the processes that shape comets within our own system, preserving ancient materials that may hold clues to the formation of planetary systems, the distribution of organic molecules, and even the origins of life itself. As it hurtles toward perihelion, its closest approach to the Sun on 29 October 2025, scientists and stargazers alike turn their gaze skyward, eager to unravel the mysteries of this celestial stranger. As 3I Atlas ventured into the inner solar system, its identity as a comet became increasingly evident. Unlike asteroids, which are rocky remnants of planetary formation, comets are icy bodies that originate from the frigid outer reaches of star systems. When they approach a star, the heat sublimates their volatile ices, creating a glowing coma of gas and dust that surrounds the nucleus, the comet's solid core. For 3I Atlas, this process began As it neared the Sun, its hyperbolic trajectory, drawing it closer to the solar warmth, observations revealed a coma and a faint, elongated tail, confirming its classification as a comet rather than an asteroid. However, determining the size of its nucleus proved challenging, as the light from the coma overwhelmed the faint glow of the nucleus itself. Estimates from the Hubble Space Telescope suggest a nucleus ranging between 0.32 and 5.6 kilometers diameter, with a most probable size under 1 kilometer. This relatively modest size, combined with its high velocity, paints a picture of a fragile yet resilient object, surviving the harshness of interstellar travel. The comet's activity is driven entirely by the Sun. As 3I Atlas approached the inner solar system, solar radiation heated its surface, causing the ices within its nucleus to sublimate directly into gas. This process released not only water vapor but also carbon dioxide, carbon monoxide, and other volatile compounds which carried dust particles into space, forming the coma. Spectroscopic analyses by the James Webb Space Telescope, JWST, revealed an unusual chemical signature, an abundance of carbon dioxide, and traces of water ice, water vapor, and carbonyl sulfide. Such a composition differs from many solar system comets, suggesting that 3I Atlas formed inches a different environment, possibly one with a distinct chemical history shaped by the conditions of its home star system. Additionally, observations by the Very Large Telescope detected emissions of cyanide gas and atomic nickel vapor, concentrations comparable to those seen in Inch's comets within our own system. These findings hint at a complex internal structure and a history of exposure to extreme temperatures and pressures, perhaps during its formation or subsequent encounters with stellar winds or magnetic fields. Despite its scientific intrigue, 3I Atlas remains a faint object in Inch's Earth skies. At its brightest, it is expected to reach an apparent magnitude of 11.5, far too dim for the unaided eye to detect. Observers using small telescopes or advanced astrophotography equipment will have the best chances of glimpsing its ghostly glow, particularly during the months leading up to and following its perihelion passage. From July to September 2025, 3I Atlas will traverse the constellations Sagittarius, Ophiuchus, Scorpius, and Libra, its position shifting against the dense backdrop of the Milky Way. However, its proximity to the galactic center, a region crowded with stars, complicates observations, as the comet's light often blends with the faint glimmers of distant stars. As it approaches perihelion Inch's October, the comet's solar elongation, the angle between the Sun and the comet as viewed from Earth, will shrink, limiting visibility to equatorial regions just after sunset. After passing perihelion, 3I Atlas will re-emerge Inch's the pre-dawn sky, gradually fading as it retreats from the Sun's influence. Yet even as its light dims, the data it leaves behind will illuminate the enigmatic nature of interstellar comets and the stories they carry across the cosmos. The origin of 3I Atlas is a tale etched Inch's the motions of stars and the gravitational tides of the Milky Way. Tracing its path backward through the void reveals a trajectory that diverges sharply from the orderly orbits of solar system objects. Instead, it originates from the southern celestial hemisphere, a region of the galaxy where the thick disk, a sprawling, ancient component of the Milky Way, dominates the stellar landscape. This structure, distinct from the younger, flatter, thin disk where our Sun resides, is a repository of stars over 7 billion years old, their metallicities reflecting the chemical evolution of the galaxy Inch's its early epochs. For 3I Atlas, this places its birth Inch's a cosmic cradle of antiquity, where the conditions of star formation and planetary system development may have differed significantly from those Inch's our own corner of the galaxy. The comet's velocity components provide further insight into its galactic heritage. In the galactic coordinate system, its motion is characterized by three key velocities: radial velocity u, transverse velocity volts, and vertical watts. Upon entering the solar system, 3I Atlas possessed a radial velocity of u, mid 51.0 kilometers per second, indicating it was moving away from the galactic center at a substantial pace. Simultaneously, its vertical velocity of watts below 18.5 kilometers per second reveals a trajectory that is tilted relative to the galactic plane, a hallmark of the thick disk population. Unlike the thin disk, where stars and objects tend to orbit inches a relatively flat plane, the thick disk is a dynamic three-dimensional structure. Its inhabitants, including 3I Atlas, follow inclined or eccentric paths, often crossing the galactic midline at high altitudes. This vertical motion suggests that the comet's parent star system, if such a system exists, may have resided inches a region where gravitational interactions with other stars, dark matter, or galactic spiral arms played a role, inches ejecting it into interstellar space. The age of 3I Atlas, estimated to range between 3 and 14 billion years, adds another layer of intrigue to its story. This timescale aligns with the typical lifespans of thick disk stars, many of which formed inches the Milky Way's tumultuous early history, when supernovae and star-forming regions sculpted the galaxy's structure. If the comet is indeed as old as the upper end of this range, it predates the formation of the solar system by nearly 3 billion years, making it one of the oldest objects ever observed. Such an ancient origin raises profound questions about the survival of comets inches interstellar space. Traditionally, comets are considered fragile bodies, vulnerable to erosion from stellar radiation and collisions with interstellar dust. Yet 3I Atlas has endured eons of travel, its nucleus intact and its chemistry largely preserved. This resilience challenges existing models of comet longevity, suggesting that some interstellar comets may serve as cosmic vaults, safeguarding materials from the earliest phases of planetary formation. The implications of 3I Atlas's age extend beyond its own history. As a relic of the Milky Way's infancy, it offers a unique window into the chemical and physical conditions of a distant era. The presence of carbon dioxide, water ice, and other volatiles inches its coma, hints at a formation environment where temperatures and pressures allowed for the condensation of these substances. In contrast to the icy reservoirs of the solar system's Kuiper belt and Oort cloud, which formed inches a relatively stable, low metallicity environment, 3I Atlas may have originated inches a star-forming region, rich inches heavier elements. Such a scenario would align with the thick disk's higher metallicity compared to the ancient halo of the galaxy, a population of stars even older than the thick disk. The comet's chemical composition could thus reflect the nucleosynthetic processes of its host star system, offering clues about the prevalence of organic molecules and prebiotic chemistry inches the early universe. Furthermore, 3I Atlas's trajectory through the solar system provides a rare opportunity to study the dynamics of interstellar objects. Unlike 1I Oumuamua and 2I Borisov, which originated from directions aligned with the solar apex, the point inches the sky toward which the sun is moving relative to nearby stars. 3I Atlas hails from the opposite hemisphere. This asymmetry inches the origins of interstellar visitors, challenges assumptions about the uniformity of interstellar object populations. Are such objects evenly distributed across the galaxy, or do they cluster inches specific regions shaped by stellar density and gravitational interactions? The discovery of 3I Atlas suggests that the thick disk may be a significant source of interstellar comets, a hypothesis that could reshape our understanding of how planetary systems form and evolve inches diverse galactic environments. Perhaps most tantalizing is the possibility that 3I Atlas is not an isolated anomaly, but part of a broader population of interstellar comets yet to be discovered. Its detection by the Atlas survey underscores the importance of wide-field telescopes, inches identifying transient phenomena, particularly those that pass close to the galactic center, where dense star fields obscure faint objects. Future surveys, equipped with more sensitive instruments and advanced algorithms for tracking interstellar trajectories. For now, however, 3I Atlas stands alone as a testament to the enduring mystery of the cosmos, a traveler from the depths of time, whispering its ancient secrets to those who dare to listen. While the age and origin of 3I Atlas offer a glimpse into the distant past, its chemical composition tells an equally compelling story, one that transcends the boundaries of its birthplace and speaks to the diversity of planetary systems scattered across the galaxy. The gases and ices detected inches its coma, from carbon dioxide to cyanide, are not merely the byproducts of solar heating, but the echoes of a star system's unique history. These molecules, forged inches the crucibles of stellar nurseries, and shaped by the gravitational tides of distant worlds, carry signatures that may differ starkly from those found inches, solar system comets. As scientists analyze these spectral fingerprints, they begin to piece together a portrait of an alien chemistry, one that could challenge existing models of planetary formation and the universality of the building blocks of life. This transition from origin to chemistry marks a shift in Inch's perspective, from understanding where 3I Atlas came from to deciphering what it is made of. The comet's journey through interstellar space has preserved these materials in a state of deep freeze, shielding them from the disruptive forces that often erase the traces of cosmic history. Yet, as it approaches the sun, the very act of sublimation becomes a tool for revelation, releasing these ancient compounds into the vacuum and allowing them to be studied in exquisite detail. What lies ahead is not merely an exploration of a single comet, but a voyage into the molecular heart of the universe, where the ingredients of worlds are laid bare. In the vast expanse of the cosmos, where celestial bodies drift silently through the void, 3I Atlas emerged as an extraordinary visitor from beyond our solar system. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, stationed at Rio Hurtado, Chile, this interstellar comet marked a significant milestone in our understanding of the universe. Unlike the countless asteroids and comets that originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas hailed from the far reaches of interstellar space, bearing the unmistakable signature of an object born in another planetary system. Its arrival was heralded by an unbound trajectory, a hyperbolic path that defied the gravitational pull of the sun. As it swept through the inner solar system, 3I Atlas carried with it the secrets of a star system long removed from our own, offering scientists a rare opportunity to study material that had never before entered our cosmic neighborhood. At the time of its discovery, 3I Atlas was already hurtling through space at an astonishing velocity, over 58 kilometers per second relative to the sun. This blistering speed was a clear indication that the comet had not originated from the solar system itself, as no native object possesses such a high hyperbolic excess velocity. Instead, it had been flung into interstellar travel by the gravitational forces of its home star system, perhaps ejected during a chaotic planetary migration or a violent encounter between celestial bodies. The fact that it had not been gravitationally bound to the sun meant that 3I Atlas would not remain in the solar system indefinitely. It would eventually escape back into the depths of space, continuing its journey toward the unknown. Yet for a brief moment in time, it became a cosmic messenger, offering insights into the conditions that shape distant worlds. As one of only 3 confirmed interstellar objects to ever be observed passing through the solar system, 3I Atlas followed in the footsteps of 1I Oumuamua and 2I Borisov. While Oumuamua had been a rocky enigma, its nature debated among scientists, and Borisov had displayed the familiar traits of a comet. 3I Atlas presented an entirely new chapter in the story of interstellar visitors. Unlike the others, it was not just a passive wanderer, but an active comet, its nucleus releasing plumes of gas and dust as it was heated by the sun's radiation. This activity allowed astronomers to study its composition in ways that had not been possible with its predecessors, revealing a chemical profile unlike anything seen in native comets. The presence of carbon dioxide, water ice, and other volatile compounds hinted at a formation environment that differed from the Kuiper Belt, suggesting that 3I Atlas had once orbited a star under different physical and chemical conditions. Beyond its immediate characteristics, the significance of 3I Atlas lay in its age. Estimates placed its origins at over 7 billion years ago, predating the solar system by nearly 3 times its current age. This staggering antiquity meant that 3I Atlas had traveled through the Milky Way for eons, surviving encounters with stellar winds, magnetic fields, and the gravitational tides of the galaxy. Its arrival in our system was not merely a fleeting event, but the culmination of a cosmic journey spanning billions of years. As scientists traced its path backward through the stars, they sought to uncover the mysteries of its birthplace, and the history of its travels. In doing so, 3I Atlas became more than just a comet. It became a relic of a bygone era, a tangible piece of the universe's deep past, now passing briefly through our own backyard. As 3I Atlas ventured deeper into the inner solar system, its true nature began to unfold. Unlike the asteroids and native comets that orbit the Sun inches predictable, elliptical paths, this interstellar visitor possessed a distinct structure shaped by the conditions of its distant home. At its core lay a solid icy nucleus, a frozen relic of a star system long removed from our own. Though the exact dimensions of the nucleus remained uncertain, observations by the Hubble Space Telescope suggested a range of sizes, from a modest 0.32 kilometers to a more substantial 5.6 kilometers inches diameter. However, the true size of the nucleus proved elusive, as the light it emitted was often obscured by the surrounding coma, a luminous cloud of gas and dust that formed as the comet approached the Sun. This dynamic interaction between the nucleus and the coma was central to 3I Atlas's activity, marking it as a true comet rather than a lifeless asteroid. The process of sublimation played a crucial role, inches shaping 3I Atlas's appearance. As the comet neared the Sun, the increasing solar radiation caused the ice on its surface to transition directly from a solid to a gaseous state, bypassing the liquid phase entirely. This transformation released a steady stream of volatile compounds, including water vapor, carbon dioxide, and other trace gases, which carried with them fine particles of dust lifted from the nucleus. Together, these elements formed the coma, an ethereal halo that surrounded the comet like a ghostly aura. The coma was not static, it expanded and evolved as the comet continued its journey, shifting inches density and composition as different layers of ice beneath the surface were exposed. This continuous outgassing created a mesmerizing spectacle, as the comet's head shimmered with the glow of escaping volatiles, illuminated by the distant Sun. Among the most striking revelations about 3I Atlas came from the James Webb Space Telescope, which detected an unusual richness of carbon dioxide within its coma. While native comets typically contained a mix of water ice, methane, and ammonia, the abundance of CO2 inches, 3I Atlas suggested a formation environment markedly different from the Kuiper Belt. This finding pointed to a possible origin inches a colder, more chemically distinct region of its home star system, one where temperatures were low enough to allow carbon dioxide to remain inches a frozen state, unlike inches the warmer inner regions of the solar system. Additionally, observations by the Very Large Telescope revealed the presence of cyanide gas and atomic nickel vapor, compounds that are rarely encountered inches native comets. These elements hinted at a formation process that involved a unique combination of temperature, pressure, and chemical interactions, further reinforcing the idea that 3I Atlas had not originated from our own cosmic neighborhood. Despite its intrinsic beauty, 3I Atlas remained a challenging object to study. The difficulty inches distinguishing the nucleus from the coma meant that many aspects of its internal structure remained shrouded inches mystery. Scientists relied on indirect methods to estimate the size of the nucleus, analyzing how the coma expanded and how the comet's brightness changed over time. The lack of direct imaging added an element of uncertainty to the calculations, making it all the more remarkable that researchers could extract meaningful insights from such a distant and fleeting visitor. Even as 3I Atlas continued its journey through the solar system, its presence served as a reminder of the vast and varied processes that shape the cosmos. Each observation brought new clues, each spectrum a whisper from a world we had never seen, yet could now begin to understand. The chemical composition of 3I Atlas offers a tantalizing glimpse into the conditions of its distant origin, revealing a profile that diverges significantly from the comets native to our solar system. While native comets typically contain a mixture of water ice, methane, ammonia, and other volatile compounds, 3I Atlas stands apart due to its unusual richness inches carbon dioxide and the presence of rare elements such as cyanide and atomic nickel. These findings suggest that the comet formed inches an environment with a distinct chemical makeup, possibly under conditions of extreme cold and isolation. Such an environment may have existed inches the outer reaches of its home star system, where temperatures were low enough to preserve volatile compounds inches their frozen states. The abundance of carbon dioxide, inches particular, indicates that 3I Atlas may have originated inches a region of its planetary system where CO2 ice played a dominant role, inches the formation of small bodies, a stark contrast to the more water-dominated comets of the Kuiper belt. The detection of cyanide gas and atomic nickel vapor further underscores the uniqueness of 3I Atlas's chemical signature. Cyanide, a compound composed of carbon and nitrogen, is typically associated with organic chemistry and plays a fundamental role in the formation of amino acids, the building blocks of life. Its presence in the comet's coma suggests that 3I Atlas may carry traces of the same chemical precursors that contributed to the emergence of life on Earth. Atomic nickel, on the other hand, is an element that tends to form high temperature environments, such as the interiors of stars or during supernova explosions. The fact that nickel vapor has been observed the comet's outgassing implies that the comet may have formed a region where such elements were present higher concentrations than our own solar system. This raises intriguing questions about the chemical diversity of planetary systems beyond our own, and whether such exotic materials might be more common in the cosmos than previously assumed. These differences in composition point to a broader possibility that planetary systems throughout the galaxy may exhibit a wide range of chemical compositions, shaped by the specific conditions under which they formed. In our own solar system, the distribution of elements is largely determined by the early stages of planetary formation, with heavier elements concentrated in the inner regions and lighter, volatile compounds prevailing in the outer reaches. However, if 3I Atlas is representative of a class of comets from other star systems, it suggests that such variations may be the norm rather than the exception. Some planetary systems may have formed regions of the galaxy where different combinations of elements were available, leading to the development of comets with entirely different chemical profiles. Others may have experienced more turbulent evolutionary histories, with collisions and migrations altering the distribution of materials in ways that differ from our own cosmic neighborhood. Understanding the full extent of this chemical diversity is essential for unraveling the broader story of planetary formation and the potential for life beyond Earth. One of the most profound implications of 3I Atlas's chemical composition is the possibility that interstellar comets may serve as cosmic couriers of exotic materials, capable of seeding young planetary systems with substances that are otherwise rare or absent. In the early days of planetary formation, when nascent worlds were still gathering mass and sorting out their chemical inventory, comets like 3I Atlas could have delivered crucial ingredients necessary for the development of life. The presence of cyanide in its coma, for instance, hints at the potential for such comets to contribute to the synthesis of organic molecules, which are essential for biochemistry. If comets from other star systems frequently interact with young planets, as is likely in the dense regions of the galaxy, they may play a significant role in shaping the chemical landscapes of entire planetary systems. This raises the possibility that the building blocks of life may not have originated solely within our solar system, but may instead have been delivered by interstellar visitors like 3I Atlas. Furthermore, the study of 3I Atlas provides a window into the chemical evolution of the universe itself. The presence of certain elements and compounds in the comet's coma reflects the conditions that existed in its home star system billions of years ago, offering a snapshot of the chemical processes that occurred in the early stages of planetary formation. By comparing the chemical signatures of interstellar comets with those of native comets, scientists can begin to reconstruct the history of elemental distribution across the galaxy. This knowledge is not only valuable for understanding the origins of our own solar system, but also for identifying the types of planetary systems that may be most conducive to the emergence of life. If future observations reveal that interstellar comets commonly carry a rich array of volatile compounds and organic materials, it could suggest that the necessary ingredients for life may be widespread throughout the cosmos, carried on the tails of ancient comets as they traverse the galaxy. The journey of 3I Atlas through the solar system is thus more than just a fleeting encounter with a distant visitor. It is a rare opportunity to study the chemical legacy of a star system that has long since faded into the void. Every spectral line captured by telescopes, Every trace of gas and dust released by the comet tells a story of a world that once orbited a long-dead star. As scientists continue to analyze the data gathered from this interstellar traveler, they may uncover new insights into the chemical diversity of the universe and the intricate web of connections that bind together the stars, planets, and comets that populate the cosmos. Despite its significance, 3I Atlas presented a formidable challenge to observers. Its intrinsic faintness, coupled with its position near the crowded heart of the Milky Way, made it a difficult target, even for the most advanced telescopes. With an apparent magnitude of no brighter than 11.5 at its peak, the comet remained invisible to the naked eye and beyond the reach of casual stargazers peering through modest binoculars. Only specialized instruments equipped with sensitive detectors and large apertures could hope to capture its elusive glow. Observers relying on plate-solving smart telescopes needed at least a 3 to 4.5 inch, 7.6 to 11.4 centimeter aperture to detect the comet's diffuse light, a testament to the immense distances it traversed through space. Even with such equipment, tracking 3I Atlas demanded patience and precision, as its slow movement against the backdrop of stars required careful calibration and long exposure times to distinguish its faint coma from the surrounding stellar field. The comet's journey through the night sky unfolded, inches a slow and deliberate manner. Beginning inches the constellation Sagittarius, where it appeared as a mere smudge of light against the dense tapestry of the galactic center. In the first half of July 2025, 3I Atlas lingered near the border of Sagittarius and Serpens Cauda, its apparent magnitude hovering at 17.5, a level so faint that it was barely distinguishable from the background noise of distant stars. As the weeks progressed, the comet gradually brightened, shifting eastward through Ophiuchus and Scorpius before settling into Libra by late August. By mid-September, its brightness had climbed to magnitude 14, making it marginally easier to observe with dedicated amateur setups. Yet, despite this gradual increase in its luminosity, 3I Atlas remained an elusive presence, its light constantly battling against the glare of the Milky Way and the limitations of atmospheric interference. The greatest challenge to observing 3I Atlas arose as it approached perihelion inches, October 2025. As it neared the Sun, the comet's solar elongation diminished, reducing its visibility to only equatorial regions and limiting observation windows to brief moments just after sunset. From 1 October to 9 November, the comet remained less than 30 degrees from the Sun inches the sky, rendering it effectively invisible to ground-based observers. This period of solar conjunction meant that 3I Atlas passed behind the Sun from Earth's perspective, vanishing from view as it completed its closest approach. However, the situation was not entirely dire. While terrestrial telescopes were unable to track the comet during this phase, Mars-based orbiters presented a rare opportunity to study it in detail. From the red planet's vantage point, 3I Atlas was expected to reach an apparent magnitude of 11, a brightness sufficient for imaging by orbiting spacecraft. This interplanetary perspective offered a unique chance to gather data on the comet's behavior as it neared the Sun, filling inches a critical gap inches our understanding of its activity and composition. Following its perihelion passage, 3I Atlas re-emerged inches the dawn sky, becoming visible once again inches November 2025. As it receded from the Sun, the comet gradually faded, its brightness dropping below magnitude 12 by December. During this final leg of its journey, 3I Atlas traced a path through the constellations Virgo and Leo before vanishing into the darkness of the outer solar system. Its departure marked the end of a fleeting encounter with Earth, a rare interstellar visitor that had briefly illuminated the night sky before resuming its endless voyage through the cosmos. For those who had managed to catch a glimpse of its ghostly glow, 3I Atlas stood as a testament to the vastness of the universe and the enduring mystery of its hidden wonders. In the vast expanse of the cosmos, where silence reigns supreme and light travels for millennia before reaching human eyes, the detection of 3I Atlas was akin to catching the faintest whisper inches an ocean of noise. On 1 July 2025, deep inches the arid expanse of northern Chile, the asteroid terrestrial impact last alert system, Atlas scanned the night sky with its twin telescopes, searching for the faintest traces of celestial motion. The Atlas system, designed to detect potentially hazardous asteroids, is a sentinel of vigilance, tirelessly scanning the heavens for signs of disruption. Yet on that particular night, its sensitive optics captured something far more enigmatic, a point of light, barely perceptible against the backdrop of the Milky Way's dense star fields. The signal was subtle, buried beneath the brilliance of countless stars, but its motion betrayed a secret. It was not bound to the solar system. At the moment of its discovery, 3I Atlas was already hurtling through space at a blistering speed of 61 kilometers per second. Its path slicing through the outer reaches of the solar system, at a distance of 4.5 astronomical units from the Sun. This meant it had already traveled far beyond the orbit of Jupiter, where the gravitational pull of the planets is weak and the Sun's influence wanes. From Earth's perspective, the object appeared as a faint smudge inches the constellation of Sagittarius, nestled among the crowded stellar tapestry near the galactic center. The sheer density of stars inches that region made detection all the more challenging. As 3I Atlas moved like a ghost through a sea of brilliance, its faintness, measured at an apparent magnitude of 18, placed it far below the threshold of human vision, requiring the keen eyes of robotic telescopes to discern its presence. Yet the discovery of 3I Atlas was not a mere stroke of luck. It was the result of decades of refinement, inches observational astronomy, a testament to the ingenuity of those who seek to map the heavens with ever greater precision. The Atlas system, though primarily designed to identify Earth-threatening asteroids, operates on the same principles that allow astronomers to uncover the most elusive objects inches the cosmos. Its ability to detect faint moving objects is a product of advanced image processing algorithms and automated data analysis, tools that transform raw pixel data into meaningful astronomical insights. When the system flagged this faint anomaly, it triggered a cascade of follow-up observations, each one peeling back another layer of the mystery surrounding 3I Atlas. The initial data suggested a highly unusual trajectory, one that deviated from the elliptical paths of most solar system objects. While comets typically follow elliptical orbits that bring them repeatedly into the inner solar system, 3I Atlas was on a hyperbolic path, meaning it would not return. Its velocity alone was enough to confirm that it was not a native of the solar system. The Sun's gravity, while immense, could not hold onto an object moving at nearly 58 kilometers per second relative to the Sun. This realization sparked a wave of excitement among astronomers, as it signaled the arrival of a visitor from interstellar space, an object born inches another star system, carried across the void by the relentless pull of cosmic forces. What made 3I Atlas even more remarkable was the uncertainty surrounding its true nature. At first, it was unclear whether it was an asteroid or a comet. Unlike asteroids, which are rocky bodies devoid of volatile ices, comets are composed of frozen gases and dust that sublimate when exposed to the sun's warmth. The absence of visible outgassing inches early observations left astronomers divided. Some believed it was a dormant asteroid, while others speculated that its faint coma, only marginally detectable, was evidence of its true identity. The debate continued until further observations revealed the telltale signs of a comet, a faint halo of gas and dust, and a slight elongation suggesting the beginnings of a tail. These features confirmed that 3I Atlas was not merely a wanderer from another star system, but a comet, a frozen relic carrying the secrets of its distant origins. The confirmation of 3I Atlas's interstellar status was a triumph of modern astronomy, a demonstration of how technological progress allows us to peer deeper into the cosmos than ever before. Yet it also raised profound questions. What kind of environment could have produced such an object? Where inches the galaxy did it originate? And what could its journey through interstellar space reveal about the processes that shape planetary systems across the universe? As the data poured inches, one thing became clear. 3I Atlas was not just another celestial body, it was a messenger from the stars, bearing witness to the vast and uncharted realms beyond our own. The initial observations of 3I Atlas sparked a flurry of activity among astronomers, who quickly mobilized to gather more data on the enigmatic object. Within days of its discovery, follow-up observations from multiple observatories around the world began to refine its trajectory, revealing the unmistakable signature of an interstellar visitor. The Minor Planet Center, MPC, the authoritative body responsible for tracking minor bodies, inches the solar system, initially listed 3I Atlas on the Near-Earth Object Confirmation page due to concerns that its path might bring it dangerously close to Earth. However, as more precise orbital calculations emerged, it became evident that the object would never come closer than 1.8 astronomical units from our planet, eliminating any immediate threat. More importantly, the refined trajectory confirmed what early data had suggested. 3I Atlas was on a hyperbolic path, meaning it would not return to the solar system and had originated from beyond our cosmic neighborhood. To verify this conclusion, astronomers turned to a network of ground-based and space-based telescopes, each contributing a piece to the growing picture of 3I Atlas's identity. The Zwicky Transient Facility, ZTF, at Palomar Observatory, Inches, California, played a crucial role, Inches reconstructing the comet's early movements by analyzing archival images taken just days before the official discovery. ZTF confirmed that 3I Atlas had been present Inches the sky as early as 14 June 2025, albeit at a much fainter magnitude. This revelation was significant, as it demonstrated that the object had been undetected, despite passing through regions of the sky that are regularly monitored. The reason for this oversight lay Inches the extreme density of stars near the galactic center, where 3I Atlas had spent much of its observable time. The sheer number of stars Inches that region overwhelmed the sensitivity of existing survey telescopes, effectively masking the comet's presence until it had moved into a clearer portion of the sky. Amateur astronomers also played a pivotal role, Inches unraveling the mystery of 3I Atlas. One such individual, Sam Dean, meticulously examined Atlas data archives and identified additional pre-discovery observations dating back to 5 June 2025. His findings helped extend the timeline of 3I Atlas's journey through the solar system, allowing scientists to calculate its trajectory with greater accuracy. These contributions underscored the growing importance of citizen science Inches modern astronomy, as the collective efforts of professional and amateur observers alike expanded the reach of astronomical research beyond the confines of large institutions. As the comet drew closer to the Sun, the defining characteristics of a comet began to emerge. On 2 July 2025, the Deep Random Survey X09 at Chile, the Lowell Discovery Telescope G37, Inches, Arizona, and the Canada-France-Hawaii Telescope T14 on Mauna Kea, all captured images showing a faint coma encircling the nucleus of 3I Atlas. The coma, a cloud of gas and dust, released as the sun's heat sublimated volatile ices on the comet's surface, provided irrefutable evidence of its cometary nature. Additionally, a subtle elongation of approximately 3 arc-seconds suggested the tentative formation of a tail, a feature commonly associated with comets as they interact with the solar wind. These observations were critical, Inches confirming that 3I Atlas was not an asteroid but a genuine comet, one that had traveled across interstellar space before entering the solar system. With the comet's identity firmly established, the Minor Planet Center formally classified 3I Atlas as the third confirmed interstellar object to visit our cosmic neighborhood, assigning it the designation 3I. This classification placed it alongside its predecessors, 1I Oumuamua, discovered Inches 2017, and 2I Borisov, discovered Inches 2019, each representing a unique window into the diversity of objects that exist beyond our solar system. The naming process followed the standard conventions for comets, and on 2 July 2025, the MPC officially designated the object as CEAS 2025 N1 Atlas, acknowledging the role of the Atlas system Inches its discovery. By the time of its formal designation, over 120 observations from 31 different observatories had been compiled, forming a comprehensive dataset that would guide future studies of the comet's behavior. The confirmation of 3I Atlas's interstellar status marked a milestone, Inches the field of planetary science, reinforcing the notion that objects from other star systems occasionally drift into the solar system. Yet, as the data accumulated, it became increasingly clear that 3I Atlas was unlike its interstellar predecessors, Inches several key ways. Its origin, composition, and trajectory all hinted at a story that extended far beyond the simple act of discovery. With each new observation, the veil of mystery surrounding this celestial wanderer thinned, revealing a cosmic traveler that carried the echoes of a distant past. The discovery of 3I Atlas underscores a fundamental truth about the universe. We see only a fraction of what exists. The cosmos is teeming with objects, many of which elude our detection due to their faintness, their position inches crowded starfields, or their fleeting passage through the solar system. 3I Atlas, with its dim magnitude and trajectory through the dense heart of the Milky Way, exemplifies the challenges faced by astronomers seeking to uncover the hidden depths of space. Its detection was a triumph of modern technology, but it also serves as a reminder of how much remains unseen. The fact that it passed undetected for several weeks, despite being monitored by some of the most powerful telescopes on Earth, suggests that many more interstellar objects may be drifting through the solar system unnoticed. One of the primary obstacles inches detecting interstellar objects like 3I Atlas lies inches their intrinsic faintness. The comet was observed at an apparent magnitude of 18, making it thousands of times dimmer than the faintest stars visible to the human eye. At this level of brightness, it required the use of specialized telescopes equipped with sensitive digital cameras and automated software to distinguish it from the overwhelming background of stars. The crowded nature of the galactic center further complicated matters. In that region of the sky, the density of stars is so great that individual objects are often lost inches the glare of their neighbors. This phenomenon, known as blending, occurs when the light from multiple sources overlaps inches a single pixel of an image, making it difficult to isolate a single moving object. 3I Atlas spent a significant portion of its observable time inches precisely such an environment, where its faint glow was masked by the brilliance of the stars behind it. Even when an interstellar object does emerge from obscurity, detecting it requires a combination of luck and preparation. Many of the telescopes used to search for transient objects operate on automated systems that scan the sky for changes over time. These systems rely on comparing successive images of the same patch of sky to identify moving targets. However, the efficiency of these surveys depends heavily on factors such as the object's brightness, its rate of motion, and the sensitivity of the instrument. Smaller telescopes with limited field of view may miss an object entirely if it passes through their field too briefly, or at an angle that makes it indistinguishable from a background star. Larger surveys, such as the Zwicky Transient Facility SAISHN and the upcoming Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, offer improved chances of detection due to their broader coverage and faster data processing capabilities. Still, even with these advancements, the sheer volume of data generated by these surveys presents a formidable challenge. Sorting through millions of images to identify genuine celestial events requires sophisticated machine learning techniques and extensive manual verification. The limitations of current detection methods highlight the need for more advanced observational tools. The Vera-C, Rubin Observatory, scheduled to begin operations inches the coming years, represents a major leap forward inches this regard. Equipped with an 8.4-meter mirror and a state-of-the-art 3,200 megapixel camera, the telescope will conduct a deep, wide-field survey of the southern sky, capturing images of the entire visible region every few nights. This unprecedented cadence will significantly improve the chances of detecting faint interstellar objects before they vanish from view. Additionally, the LSST's data processing pipeline will utilize artificial intelligence to rapidly flag potential transient events, reducing the time needed to confirm the existence of newly discovered objects. If 3I Atlas had been observed by the Rubin Observatory, it is likely that its presence would have been detected earlier and perhaps even identified as an interstellar object before its full trajectory became clear. Beyond technological improvements, the discovery of 3I Atlas also underscores the importance of global collaboration in astronomy. The confirmation of its interstellar status was the result of a coordinated effort between professional and amateur astronomers, each contributing observations that help piece together the comet's path. This collaborative model is becoming increasingly vital as the scale of astronomical surveys grows. The sheer volume of data being collected necessitates a distributed approach to analysis, where contributions from multiple observers help fill gaps in coverage and provide redundant verification of key findings. In the case of 3I Atlas, the input of individuals like Sam Dean, who combed through archival data to uncover pre-discovery observations, was instrumental in refining the comet's trajectory and understanding its origins. As we look to the future, the lessons learned from 3I Atlas will shape the way we search for interstellar objects. The realization that such objects may be more numerous than previously thought, combined with the limitations of current detection methods, suggests that we are only beginning to scratch the surface of what lies beyond our solar system. The next generation of telescopes, operating with greater sensitivity and coverage, will undoubtedly reveal many more interstellar visitors, each one offering new insights into the processes that govern the formation and evolution of planetary systems across the galaxy. In the grand cosmic theater, 3I Atlas is but one actor, a fleeting guest, whose brief appearance reminds us that the universe is far vaster and more mysterious than we can yet comprehend. As the study of interstellar objects advances, a compelling narrative begins to take shape, one that stretches across the vast distances between stars and into the depths of cosmic history. 3I Atlas, now joined by its predecessors, 1I Oumuamua and 2I Borisov, forms a growing catalogue of celestial wanderers that offer a glimpse into the dynamic processes shaping planetary systems throughout the galaxy. Yet despite their shared interstellar origins, these objects differ in striking ways, raising intriguing questions about the environments from which they came and the mechanisms that propelled them into the void. The similarities and contrasts among these three interstellar visitors suggest a complex cosmic tapestry, where the birthplaces of planets, the ejection of material from young star systems, and the gravitational tides of the galaxy itself conspire to send these objects on their lonely journeys. Of the three confirmed interstellar objects, 1I Oumuamua stands apart as the most enigmatic, discovered in October 2017. It presented a mystery that defied easy categorization. Initially thought to be an asteroid due to its lack of visible coma or tail, Oumuamua exhibited an unusual acceleration as it departed the solar system, leading to speculation that it might be a comet undergoing outgassing or even a man-made object. However, subsequent studies ruled out the latter possibility, leaving its true nature still debated. Its elongated shape, estimated to be roughly 10 times longer than it is wide, further complicated its classification. Unlike 3I Atlas, which displayed clear cometary activity, Oumuamua remained largely inert, offering little the way of clues about its composition or origin. This contrast with 3I Atlas, which actively released gas and dust as it approached the Sun, highlights the diversity of interstellar objects and hints at the varied conditions under which they formed. In stark contrast to Oumuamua's ambiguity, 2I Borisov, discovered in August 2019, presented a more familiar profile. Like 3I Atlas, it was a comet that exhibited a well-defined coma and a visible tail, behaving much like the comets that originate in the outer reaches of the solar system. Spectroscopic analysis of 2I Borisov revealed the presence of water vapor and carbon monoxide, compounds commonly found in comets from our own system. This similarity suggested that 2I Borisov may have formed under conditions analogous to those in the early solar system, possibly ejected from a distant planetary system during a period of gravitational instability. Unlike 3I Atlas, however, 2I Borisov's trajectory traced a path originating from the general direction of the solar apex, the direction in which the Sun is moving relative to the surrounding stars. This alignment with the Sun's motion raised the possibility that 2I Borisov's trajectory was influenced by the same galactic dynamics that shaped the movement of stars in the Milky Way. 3I Atlas, by contrast, emerged from the opposite side of the galaxy, tracing a path that led it from the direction of the Milky Way's thick disk, a region populated by older stars. This distinction in origin immediately set it apart from both Oumuamua and 2I Borisov, suggesting that it hailed from a different stellar environment. The thick disk is characterized by a higher velocity dispersion and a greater distance from the galactic plane compared to the thin disk where most younger stars reside. The fact that 3I Atlas originated from this region implies that it may have formed Inch as a system with a different evolutionary history, one shaped by the gravitational interactions of older stars and the remnants of ancient star-forming regions. Moreover, the high vertical velocity component observed Inch's 3I Atlas's trajectory indicates that it follows an inclined orbit relative to the galactic plane, further distinguishing it from the more conventional paths of 2I Borisov and Oumuamua. The differences in Inch's composition between these interstellar objects also contribute to the growing puzzle of their origins. While 2I Borisov closely resembled Comet's Inch's our own solar system, with its water-rich composition, 3I Atlas displayed a surprising abundance of carbon dioxide and a relatively low concentration of water ice. Additionally, observations by the Very Large Telescope revealed the presence of cyanide gas and atomic nickel vapor, compounds not typically seen in Inch's, such quantities Inch's solar system comets. These chemical signatures suggest that 3I Atlas may have formed Inch as a colder or more chemically distinct environment, where different volatile materials were available for incorporation into its nucleus. The presence of nickel vapor, Inch's particular, raises intriguing questions about the physical conditions that existed Inch as its home system, as such elements are typically associated with high-temperature processes or the breakdown of refractory materials. Taken together, the distinct characteristics of 1I Oumuamua, 2I Borisov, and 3I Atlas indicate that interstellar objects do not arise from a uniform set of circumstances. Instead, they appear to be the products of diverse planetary systems, each shaped by its own unique history of formation and evolution. Some may have been ejected during violent gravitational interactions between planets, while others may have formed Inch as the outer reaches of their parent systems and later drifted into the void. The fact that these objects come from different directions Inch as the galaxy further supports the idea that they originate from a variety of stellar environments, each with its own chemical and dynamical history. As more interstellar objects are discovered, the emerging pattern suggests that the Milky Way is a dynamic and interconnected web of planetary systems, where material is constantly exchanged through the gravitational tides of stars and the sweeping arms of the galaxy. Yet, despite the growing number of interstellar objects, many fundamental questions remain unanswered. Why do some interstellar comets display such strong similarities to their solar system counterparts, while others appear to be chemically and structurally distinct? What determines the frequency with which these objects are ejected from their parent systems? And what mechanisms drive their eventual trajectories into interstellar space? Most importantly, what can these objects tell us about the formation and evolution of planetary systems beyond our own? As the study of 3I Atlas continues, and as future telescopes expand our ability to detect more interstellar visitors, these questions will only grow more pressing. The answers may lie inches the very fabric of the cosmos, waiting to be uncovered by the next generation of explorers who dare to look beyond the familiar and into the vast unknown. In the vast expanse of the Milky Way, where stars flicker like distant beacons and nebulae swirl Inch's silent symphonies, the arrival of interstellar objects stirs a profound sense of awe. These celestial wanderers, born Inches the cradles of alien star systems, drift through the void as silent witnesses to the universe's untold stories. Among them, 3I Atlas, alongside its predecessors, 1I Oumuamua and 2I Borisov, stands as a testament to the diversity of cosmic phenomena. Yet, as we gaze upon these travelers, a question lingers. Are they siblings bound by a shared origin and fate, or outliers, each forged by unique cosmic circumstances? To unravel this enigma, we must peer beyond their surfaces, into the intricate dance of their trajectories, compositions, and histories. For Inches, their differences lies a deeper truth, one that speaks to the dynamic, ever-evolving tapestry of our galaxy. The journey begins with 1I Oumuamua, the first interstellar visitor discovered Inches 2017. Its elongated, metallic form defied easy classification, sparking debates about whether it was a fragment of a shattered planet, a rogue asteroid, or something entirely novel. Then came 2I Borisov Inches 2019, a comet that bore striking similarities to the icy bodies of our own solar system. its coma and tail betraying a familiar chemistry. Now 3I Atlas arrives, a comet of peculiar composition, its carbon dioxide-rich outgassing and southern galactic origin setting it apart. Together, these three form a triad of interstellar enigmas. Each a thread inches the cosmic loom. But do they weave a pattern of kinship, or do they reflect the chaotic beauty of a universe teeming with possibility? To understand the significance of 3I Atlas, we must first revisit its predecessors. 1I Oumuamua, discovered by the Pan-STARRS telescope Inches Hawaii, was unlike anything observed before. Its cigar-shaped form, measuring approximately 400 meters inches length and 40 meters inches width, suggested a density akin to rock or metal, yet it lacked the characteristic coma and tail of a comet, leaving scientists puzzled. Was it a derelict spacecraft, a relic of an ancient civilization, or was it a natural object shaped by processes unknown to us? The absence of volatile materials and its hyperbolic trajectory, indicating an escape velocity far exceeding the gravitational pull of its home system, hinted at an origin far removed from the icy realms of protoplanetary disks. By contrast, 2I Borisov, discovered by amateur astronomer Gennady Borisov Inches 2019, was a revelation. Its coma and tail, rich inches water vapor, and carbon-based molecules mirrored those of Comet's Inches our own solar system. Borisov followed a hyperbolic path, confirming its interstellar origin, yet its behavior was eerily familiar. Spectroscopic analyses revealed similarities to Halley's Comet, suggesting that the processes shaping Comet's Inches distant star systems are not so different from those Inches our own backyard. Borisov's discovery offered a bridge between the exotic and the mundane, a reminder that the laws of physics transcend the boundaries of worlds. Now enters 3I Atlas, a comet that defies expectations. Unlike Borisov, which exhibited a water-rich coma, 3I Atlas is dominated by carbon dioxide. Observations by the James Webb Space Telescope unveiled a composition rich inches CO2, with traces of water ice, carbon monoxide, and carbonyl sulfide. More intriguingly, its southern galactic origin, a departure from the solar apex direction, predicted by many models, suggests a history distinct from its predecessors. Where Borisov hailed from the thin disk of the Milky Way, a region teeming with younger stars and ongoing star formation, 3I Atlas originates from the thick disk, a denser, older structure where stars move Inches chaotic orbits. This distinction implies that 3I Atlas may have formed Inches an environment vastly different from that of Borisov, perhaps Inches a stellar nursery long since disrupted by galactic tides. The divergence, Inches composition and origin among these three interstellar visitors paints a picture of galactic diversity. Oumuamua's rocky, metallic nature suggests a formation scenario involving high-energy collisions or extreme temperatures, while Borisov's icy profile aligns with the cold, distant reaches of protoplanetary disks. 3I Atlas, with its CO2-rich coma and ancient lineage, hints at a different epoch. Inches the galaxy's history, an era when volatile rich materials were abundant and planetary systems were still Inches their infancy. Together they challenge the notion that interstellar objects share a uniform origin, instead revealing a spectrum of possibilities shaped by the myriad ways stars and planets form, collide, and evolve. The differences among Oumuamua, Borisov, and 3I Atlas are not mere curiosities. They are windows into the mechanisms that govern the birth and death of planetary systems. The existence of interstellar objects implies that ejection is a common outcome. Inches the early stages of planetary formation. Gravitational interactions with giant planets, stellar encounters, or the chaotic accretion of material Inches nascent systems can hurl fragments into the void, where they drift as interstellar vagabonds. However, the diversity Inches their compositions and origins suggests that these ejections occur under varying conditions. Consider the case of 3I Atlas. Its residence Inches the thick disk, a population of stars billions of years old, implies that it may have formed Inches a stellar neighborhood, now long since transformed. The thick disk is a relic of the Milky Way's early days, a region where stars move Inches inclined, eccentric orbits, and where the chemical composition differs from the younger, metal-rich thin disk. If 3I Atlas indeed hails from this ancient reservoir, it may have originated Inch's a planetary system that predates the solar system itself. Such a scenario raises tantalizing questions. Could 3I Atlas be a remnant of a long-dead star system, its parent body now reduced to stardust? Or does its presence suggest that the processes of planetary formation and disruption have persisted for billions of years, continually seeding the galaxy with interstellar debris? Moreover, 3I Atlas's CO2-rich composition offers clues about the environmental conditions of its birthplace. In our solar system, CO2 is typically associated with objects from the outer Kuiper belt, where temperatures are low enough to preserve such volatile compounds. However, the abundance of CO2 Inches 3I Atlas exceeds that seen Inch's native comets, indicating a different evolutionary path. Perhaps the protoplanetary disk from which 3I Atlas emerged was richer Inch's carbon-based materials, or perhaps its parent star experienced a phase of intense stellar activity that altered its chemical makeup. Whatever the case, the comet's chemistry serves as a Rosetta Stone, decoding the history of a distant corner of the galaxy. The implications extend beyond individual objects to the broader architecture of planetary systems. The fact that interstellar comets like Borisov and 3I Atlas exhibit similarities to native comets suggests that the processes governing their formation are universal, yet the uniqueness of Oumuamua reminds us that there is no single template for planetary systems. Some may give rise to icy bodies rich Inches volatiles, while others produce rocky, metallic fragments. The diversity of interstellar visitors reflects the diversity of their homes, a galaxy teeming with stars, each with its own story to tell. Furthermore, the detection of 3I Atlas challenges assumptions about the distribution of interstellar objects. Previous models predicted that most interstellar comets would originate from the solar apex, the direction Inches which the Sun is moving through the galaxy. The southern origin of 3I Atlas, however, suggests that interstellar objects may hail from all directions depending on the dynamical history of their host systems. This realization has profound consequences for future surveys. If interstellar objects are distributed isotropically, then our ability to detect them depends not only on the sensitivity of our instruments, but also on the biases inherent in our observational strategies. The discovery of 3I Atlas underscores the importance of expanding our search to the southern skies, where interstellar visitors may lurk undetected. As we contemplate the origins and fates of 3I Atlas, Oumuamua and Borisov, we must turn our attention to the forces that propel these objects into the interstellar abyss. The hyperbolic trajectories of interstellar comets are not random. They are the result of complex gravitational interactions within their home systems, and the galactic tides that shape the Milky Way. Understanding these mechanisms is essential to unraveling the broader context of interstellar travel. How do planetary systems expel their inhabitants? What role do stellar encounters play in sculpting the trajectories of these exiles? And how do the gravitational forces of the galaxy itself influence their journeys? The answers lie in the physics of escape velocities and the invisible currents of the cosmos. Amper's planet's gravity alone cannot retain every fragment that forms within its orbit. Giant planets, with their immense masses, act as slingshots, flinging debris into interstellar space. Close encounters between stars, particularly dense stellar clusters, can also disrupt planetary systems, sending fragments careening into the void. Meanwhile, the Milky Way's gravitational field, a vast invisible web, exerts subtle but powerful influences on the motions of interstellar objects. These forces, though often imperceptible on human timescales, shape the destinies of comets like 3I Atlas over billions of years. To explore these phenomena further, we must delve into the mechanics of escape velocities, the role of stellar nurseries, and the galactic tides that govern the movements of interstellar objects. By doing so, we gain not only insight into the lives of 3I Atlas and its kin, but also a deeper appreciation for the interconnectedness of the universe. For Inches, the quiet journey of a single comet lies the echoes of countless collisions, the whispers of dying stars, and the enduring legacy of a galaxy Inches motion. This script, spanning over 3,000 words, weaves together scientific detail with a contemplative tone, adhering to the structure of introduction, explanation, exploration, exploration, and transition. It emphasizes the unique characteristics of 3I Atlas Inch's relation to its interstellar predecessors, while grounding its narrative inches, astrophysical principles, and cosmic wonder. Each section builds on the last, guiding the reader from discovery to implication and toward the next segment of inquiry. In the vast silent expanse of the cosmos, where time stretches into epochs beyond human comprehension, a traveler emerged from the shadows of interstellar space. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, or Station Inches Rio Hurtado, Chile, caught a glimpse of this enigmatic visitor. Designated initially as A11PEL3Z, the object soon revealed itself to be 3I Atlas, the third confirmed interstellar object to traverse our solar system. Its arrival was not a sudden intrusion, but a quiet, inevitable crossing of a boundary that separates the familiar from the unfathomably distant. With a speed of 61 kilometers per second over 140,000 miles per hour, it moved with the urgency of a cosmic nomad, unshackled by the gravitational embrace of any star. The discovery of 3I Atlas ignited a sense of profound curiosity. Unlike the rocky enigma of 1I Oumuamua or the gaseous spectacle of 2I Borisov, this comet carried with it a unique story. Its nucleus, cloaked inches a coma of gas and dust, hinted at a composition forged under alien conditions. Observations by the James Webb Space Telescope revealed an abundance of carbon dioxide and traces of water ice, carbon monoxide, and carbonyl sulfide chemical signatures that whispered of its birthplace inches the cold, ancient reaches of the Milky Way. As scientists tracked its journey, they realized that 3I Atlas was not merely a fleeting guest, but a messenger from a time when the galaxy was young, its origins entwined with the slow, inexorable dance of stellar evolution. Yet for all its grandeur, 3I Atlas remained elusive, faint at apparent magnitude 11.5. It required the keen eyes of automated telescopes and the patience of astronomers to follow its path, from the dense starfields of Sagittarius to the desolate voids between constellations. Its trajectory painted a line across the sky, a transient scar against the infinite canvas of the cosmos. As it approached perihelion inches October 2025, the sun's heat would awaken its icy heart, sending plumes of gas and dust spiraling into space. But for observers on Earth, the comet would vanish behind the solar glare, its closest approach hidden from view. Only Mars, its red neighbor, might witness the spectacle, offering a fleeting glimpse of a world that had traveled billions of years to arrive. This is the story of 3I Atlas, a comet born of stardust and time, a relic of the galaxy's deep past, and a testament to the boundless mysteries that lie beyond the edges of our own backyard. To understand its journey is to peer into the mechanisms that govern the universe itself, to grasp the delicate balance between gravity and velocity, the interplay of forces that shape the fates of celestial wanderers. At the heart of 3I Atlas's journey lies a fundamental truth of physics: the interplay between motion and gravity. Every object inches the universe, from the tiniest grain of cosmic dust to the most massive galaxy clusters, exists within a web of gravitational forces. For 3I Atlas, this web proved insufficient to bind it to the sun. Its velocity, 58 kilometers per second, 36 miles per second, relative to the solar system's barycenter, exceeds the escape velocity required to break free from the sun's gravitational pull. This critical threshold, calculated using Newton's law of universal gravitation, defines the boundary between captured and unbound trajectories. Just as a stone hurled from Earth must surpass approximately 11 kilometers per second to escape into space, 3I Atlas's blistering speed ensures it will not return to the inner solar system. The comet's path is described by a hyperbola, a mathematical curve that diverges infinitely rather than looping back like an ellipse. In orbital mechanics, a hyperbolic trajectory is reserved for objects that possess kinetic energy sufficient to overcome the gravitational well of their host body. For 3I Atlas, this meant a one-way passage through the solar system. By tracing its motion backward inches time, Astronomers determined that it entered the heliosphere from interstellar space, having traveled for millennia before encountering the Sun. Its trajectory, inclined at a steep angle relative to the ecliptic plane, further underscored its alien origin. While most solar system objects orbit the Sun within a relatively flat disk, 3I Atlas's path was tilted by tens of degrees, a stark reminder of its extraterrestrial provenance. The Sun's gravity, though immense, could not alter 3I Atlas's fate. The comet's hyperbolic excess velocity, the speed it would retain even if stripped of all gravitational influences, remained a constant 58 kilometers per second. This velocity, combined with its trajectory, dictated that 3I Atlas would depart the solar system with the same vigor it arrived. No planetary encounter, no gravitational slingshot could alter this course. The Sun, for all its dominion over the planets, could only briefly illuminate the comet's icy nucleus before releasing it back into the galactic void. This dynamic is governed by the principle of conservation of energy. As 3I Atlas approached the Sun, its kinetic energy increased, while its gravitational potential energy decreased. At perihelion, its closest approach to the Sun on 29 October 2025, the comet reached a distance of 1.36 astronomical units, AU, where the Sun's radiation would sublimate its ices and create a glowing coma. Yet even as it shed material and released jets of gas and dust, its total mechanical energy remained positive, ensuring its eventual escape. The Sun's gravity, while capable of shaping the comet's path, could not decelerate it enough to trap it in its orbit. Thus, 3I Atlas became a transient visitor, a cosmic fugitive whose journey would end where it began, the interstellar dark. The discovery of 3I Atlas offered more than a glimpse of an interstellar traveler. It provided a rare opportunity to study the galactic environment from which it hailed. By analyzing the comet's trajectory and velocity components, astronomers deduced that it originated from the Milky Way's thick disk, a vast spherical halo of older stars that orbits the galaxy's central bulge. Unlike the thin disk, where the Sun and most of the galaxy's younger stars reside, the thick disk is a relic of the Milky Way's violent youth. Its stars, enriched with fewer heavy elements than those inches the thin disk, are thought to have formed billions of years ago, when the galaxy was still coalescing from primordial clouds of gas and dark matter. The implications of this origin are staggering. If 3I Atlas indeed hails from the thick disk, it could be up to 14 billion years old, far older than the solar system's 4.6 billion years. Studies by Matthew Hopkins and colleagues, Inches July 2025, estimated the comet's age with 68% confidence to lie between 7.6 and 14 billion years, aligning with the typical lifetimes of thick disk stars. Independent analysis by Asta Taylor and Daryl Seligman placed its age between 3 and 11 billion years, reinforcing the notion that 3I Atlas is a relic from an epoch when the Milky Way was a crucible of star formation and galactic collisions. Such an object is a time capsule, carrying chemical and structural clues about the conditions that existed in the early universe. But perhaps the most intriguing revelation came from the comet's velocity vector. By decomposing its hyperbolic excess velocity into radial, transverse, and vertical components, researchers determined that 3I Atlas was moving away from the galactic center at 51 kilometers per second, while ascending through the galactic plane at 18.5 kilometers per second. This vertical motion places it among the rare population of thick disk objects, which trace orbits tilted relative to the galaxy's midplane. The high Watts component of its velocity, inches particular, suggests that 3I Atlas may have originated inches, a region where gravitational interactions with massive stars or dark matter halos nudged it onto its current trajectory. These findings challenge long-held assumptions about the distribution of interstellar objects. Prior to 3I Atlas, most predictions assumed that such visitors would originate from the solar apex, the direction of the Sun's motion through the galaxy. However, the comet's southern hemisphere origin defied expectations, hinting that interstellar objects from the opposite side of the galaxy may be more common than previously thought. This asymmetry raises questions about the biases inherent in observational surveys, which tend to focus on regions of the sky more accessible from Earth-based telescopes. If 3I Atlas is representative of a larger hidden population, it implies that the galaxy is teeming with unseen wanderers, each carrying fragments of its turbulent history. Moreover, the comet's chemical composition offers tantalizing hints about its birthplace. The James Webb Space Telescope's detection of carbon dioxide-rich ices and traces of carbonyl sulfide suggest that 3I Atlas formed inches a cold, low metallicity environment, a characteristic consistent with the thick disk's ancient stars. Such an origin contrasts sharply with the volatile, rich Kuiper belt objects of the solar system, which formed inches a warmer, chemically diverse region. By comparing 3I Atlas's spectrum to those of solar system comets, scientists hope to unravel the differences between planetary systems that formed under varying galactic conditions. Could other interstellar objects hold secrets about the prevalence of habitable worlds? Could their icy mantles preserve organic molecules essential to life? As 3I Atlas hurtled toward perihelion, it became clear that this comet was more than a transient phenomenon. It was a bridge between the familiar and the unknown, a cosmic artifact that demanded to be studied with every tool at humanity's disposal. Yet, its journey also highlighted the fragility of our observational capabilities. From Earth, the comet's faintness and proximity to the Sun rendered it invisible to all but the most advanced instruments. The challenge of tracking such objects underscores the vastness of the universe and the limitations of our vantage point. For all our technological prowess, we remain bound to a single pale blue dot, peering into the abyss with instruments that can barely scratch the surface of its mysteries. By October 2025, as 3I Atlas neared its closest approach to the Sun, its visibility from Earth became a fleeting promise. The comet's solar elongation, the angle between it and the Sun inches the sky, diminished to less than 30 degrees, confining its appearance to the twilight skies of equatorial regions. For most observers, it would vanish behind the solar glare, slipping into conjunction with the Sun on 9 November 2025. This disappearance was not a loss, but a redirection of perspective. While terrestrial telescopes turned away, the eyes of Mars orbiters might catch a final glimpse of the comet's coma, illuminated by the Sun's rays as it passed just 0.3 AU from the red planet. Yet the true lesson of 3I Atlas lay not inches its observable phases, but inches its ability to remind us of our place, inches the cosmic hierarchy. The comet's trajectory, shaped by forces that predate the solar system, served as a humbling testament to the universe's indifference to human concerns. It was a traveler without purpose, a relic of a time when galaxies were young and stars were forged inches chaos. Its hyperbolic path, a geometric inevitability dictated by physics, carried it toward destinations we could not comprehend. As 3I Atlas faded from view, it left behind a question that lingered inches the silence between stars. How many other interstellar wanderers have passed through the solar system unnoticed? How many more will arrive, bearing secrets written inches the languages of chemistry and motion? The answer, perhaps, lies not inches the comet itself, but inches the tools we create to seek it, and inches the imagination we bring to the act of searching. For inches the end, the universe reveals itself only to those who dare to look, to ask, and to wonder. In the vast tapestry of the cosmos, where stars burn for eons and galaxies spiral inches slow, gravitational waltzes, the arrival of 3I Atlas is a fleeting whisper, a ghostly visitor from the depths of interstellar space. Discovered inches July 2025, this comet has become a symbol of the universe's enigmatic generosity, offering a rare glimpse into a world far beyond our own. Yet for all its scientific significance, 3I Atlas remains stubbornly elusive. Its faintness, its trajectory, and its brief window of visibility conspire to render it almost invisible to human eyes. Even with the most advanced telescopes and instruments, this interstellar traveler evades our grasp, slipping through the cracks of observation like a phantom. Its story is one of cosmic irony, a relic of ancient stardust, born inches the crucible of a distant star system, now hurtling toward the Sun, yet so faint and fleeting that it demands the full power of modern astronomy to be seen at all. To understand 3I Atlas is to confront the limits of human perception and the humility required to witness the universe's most transient phenomena. The comet's journey through the solar system is a dance of extremes. It entered the inner solar system at a blistering speed of 61 kilometers per second, faster than any natural object save for the most energetic meteoroids. Its hyperbolic orbit, an open arc that will carry it back into the void, ensures that it is not bound to the sun. Instead, 3I Atlas is a transient interloper, destined to vanish into the interstellar dark. Yet even as it races through the heavens, the comet remains a shadow. At its brightest, it shines at a mere magnitude 11.5, a faint smudge of light that requires telescopes with apertures of at least 11 centimeters to detect. For the unaided eye, it is nothing more than a whisper inches the night, and for much of its passage, 3I Atlas disappears entirely, swallowed by the glare of the sun. To observe it is to wrestle with the ephemeral, to chase a star that refuses to linger. This elusiveness is not merely a matter of observational difficulty. It is a reflection of the comet's alien origins, unlike the comets of the solar system, which are born inches the distant Oort cloud and gradually perturbed into the inner solar system by gravitational tugs. 3I Atlas hails from another stellar neighborhood. Its trajectory, traced back billions of kilometers, reveals that it came from the direction of the galactic center, a region teeming with stars but shrouded inches the dense, crowded light of the Milky Way's core. Here, the interstellar medium is thick with gas and dust, and the sky is a chaotic sea of stellar brilliance. In such a place, even a comet as large as 3I Atlas could remain hidden, its icy heart cloaked inches the glare of 1,000 suns. It is only through the precision of modern astronomy, through the coordinated efforts of robotic telescopes, and the vigilance of both professional and amateur observers, that this interstellar wanderer was finally detected. Yet, detection is only the beginning. The true challenge lies inches unraveling the secrets of 3I Atlas before it slips beyond our reach. What can we learn from this ancient traveler? What does its chemistry reveal about the conditions of its birthplace? And how can we improve our ability to track such visitors inches the future? These questions hang over the comet like a veil, obscuring as much as they illuminate. As we turn our gaze to the heavens, we are reminded that the universe is not a static gallery of wonders, but a dynamic, ever-changing expanse. In 3I Atlas, we see not only a comet, but a mirror reflecting our own limitations, and perhaps a glimpse of the vast unknown that still awaits discovery. The faintness of 3I Atlas is a consequence of both its intrinsic properties and its position inches the solar system. Comets are inherently dim objects, their surfaces composed of dark, carbon-rich materials that reflect little sunlight. Even the most active comets, which develop luminous comas and tails through the sublimation of ices, remain faint unless they pass extremely close to the sun. 3I Atlas, however, never comes closer than 1.36 astronomical units, AU, between the orbits of Earth and Mars to the sun. While this distance allows some activity, it is insufficient to trigger the explosive outbursts that make comets like Hale-Bopp or Comet Neowise shine brightly. Instead, 3I Atlas glows faintly, its nucleus and coma blending into the background of the night sky. The comet's brightness is further diminished by its size. Observations from the Hubble Space Telescope suggest that the nucleus of 3I Atlas is no larger than 1 kilometer inches diameter, and possibly as small as 300 meters. For comparison, the nucleus of Halley's Comet, the most famous periodic comet, is approximately 15 kilometers long. AMPA's smaller nucleus means less surface area for ices to sublimate and less material to form a coma. AMPA's smaller nucleus means less surface area for ices to sublimate and less material to form a coma. AMPA's smaller nucleus of 3I Atlas is obscured by its own coma, making it impossible to distinguish its exact size and shape. This ambiguity adds to the challenge of studying the comet, as scientists must infer its physical properties from indirect measurements. Compounding these challenges is the comet's trajectory. 3I Atlas follows a hyperbolic orbit, a path that is not closed and will eventually carry it back into interstellar space. Hyperbolic trajectories are characterized by high velocities relative to the sun, and 3I Atlas is no exception. With a hyperbolic excess velocity of 58 kilometers per second, it is moving so quickly that it will escape the solar system entirely. never to return. This speed, while impressive, makes the comet's passage brief. Unlike periodic comets, which spend years or decades inches the inner solar system, 3I Atlas will be visible for only a few months before vanishing once more. Perhaps the most significant obstacle to observing 3I Atlas is its position relative to the Sun. For much of its journey, the comet will be located inches the daytime sky, its light drowned by the overwhelming brightness of the solar glare. The critical period for observation occurs inches the months leading up to perihelion, the point inches its orbit closest to the Sun, which takes place on 29 October 2025. During this time, 3I Atlas will appear inches the evening sky, rising just after sunset and setting shortly thereafter. However, as it approaches perihelion, its solar elongation, the angle between the comet and the Sun as viewed from Earth, will shrink dramatically. By early October, the comet will be less than 30 degrees from the Sun, a distance that places it within the Sun's glare and renders it invisible to ground-based telescopes. This solar conjunction is a cosmic game of hide and seek. From Earth, the comet will appear to vanish behind the Sun, its light blocked by the intervening mass of our nearest star. During this phase, even the most powerful telescopes on Earth or inches space will struggle to capture images of 3I Atlas. The only hope of observing the comet during its closest approach to the Sun lies Inch's spacecraft positioned on the far side of the Sun, or Inch's orbit around Mars. The latter option is particularly intriguing, as 3I Atlas will pass relatively close to Mars Inch's October 2025. From the red planet's perspective, the comet may reach a brightness of magnitude 11, making it a feasible target for orbiters equipped with sensitive cameras. These orbital dynamics highlight the precarious nature of studying interstellar objects. Unlike asteroids or planetary bodies, which can be tracked for years as they slowly drift through the solar system, comets like 3I Atlas offer only fleeting opportunities for observation. Their paths are dictated by the gravitational forces of the Sun and planets, and their activity sublimation, outgassing and dust emission is driven by proximity to the Sun. Every moment of visibility is precious, and every missed observation is a loss to our understanding of these rare visitors. The challenges posed by 3I Atlas are not merely technical, they are philosophical. The comet's elusiveness forces us to confront the limitations of our tools and the constraints of our vantage point. Earthbound observatories, no matter how advanced, are subject to the tyranny of daylight and atmospheric interference. Even the Hubble Space Telescope, which orbits above the atmosphere, cannot observe objects too close to the Sun. The James Webb Space Telescope, though sensitive to infrared light, is similarly constrained by the risk of solar radiation damage. These limitations mean that we are often blind to the most dramatic moments of interstellar visitors' journeys, their closest approaches to the Sun, where their activity peaks and their chemical signatures are most revealing. This situation raises a critical question. How can we study objects like 3I Atlas if our current instruments cannot follow them through their entire passage? One solution lies Inch's expanding our observational reach beyond Earth. Missions designed to operate Inch's the vicinity of the Sun, or Inch's deep space, could provide continuous monitoring of interstellar objects, capturing data during phases that are otherwise inaccessible. For example, a spacecraft positioned at the Lagrange point L5, which trails Earth Inch's its orbit, could track incoming objects from a stable vantage point. Alternatively, a fleet of small autonomous probes launched toward the outer solar system could serve as early warning systems, detecting interstellar visitors before they reach the inner solar system. Such initiatives would require significant investment and international collaboration, but the rewards could be immense. Another avenue for improvement lies Inch's the development of new technologies tailored to the study of faint and fast-moving objects. Adaptive optics, which correct for atmospheric distortions Inch's real time, could enhance the resolution of ground-based telescopes, allowing them to detect comets like 3I Atlas even under challenging conditions. Similarly, advancements Inch's computational astrometry automated software that identifies moving objects Inch's large datasets could enable the rapid discovery of interstellar visitors before they slip into obscurity. Machine learning algorithms trained on historical comet data might also help distinguish genuine interstellar objects from false positives, reducing the time spent on follow-up observations. The case of 3I Atlas also underscores the importance of global cooperation in astronomy. The comet's discovery and tracking involved contributions from observatories across multiple continents, from the Atlas Station in Chile to the Zwicky Transient Facility in California. This collaborative effort highlights the value of shared data and resources overcoming the logistical challenges of interstellar object research. Future discoveries may benefit from expanded networks of telescopes, particularly in the Southern Hemisphere, where 3I Atlas originated. Currently, many major observatories are concentrated in the Northern Hemisphere, leaving gaps in coverage that could be exploited by interstellar objects coming from unexpected directions. By investing in facilities in underrepresented regions, the astronomical community can improve its chances of detecting and characterizing interstellar visitors before they vanish. Beyond the realm of technology and logistics, 3I Atlas reminds us of the profound interconnectedness of the cosmos. The comet's origin in the galactic thick disk, a region inhabited by some of the oldest stars in the Milky Way, suggests that it is at least 7 billion years old. Predating the solar system itself, this ancient traveler carries with it the chemical fingerprints of a distant star system, offering clues about the conditions that existed in that corner of the galaxy long before our own sun ignited. By studying 3I Atlas, we gain not only insights into the history of its home, but also a deeper appreciation for the universality of cosmic processes. The same forces that shaped 3I Atlas' stellar winds, gravitational tides, and the slow churn of interstellar matter are at work throughout the galaxy, weaving the fabric of existence. Yet, for all its scientific promise, 3I Atlas remains a tantalizingly incomplete puzzle. Its chemical composition, as revealed by the James Webb Space Telescope and the Very Large Telescope, includes unusual ratios of carbon dioxide, water ice, and cyanide gas. These findings hint at a formation environment distinct from that of solar system comets, yet the exact mechanisms remain unclear. Was 3I Atlas sculpted by the intense radiation of a young star? Did it form in the cold, dark reaches of a molecular cloud? Or was it ejected from a planetary system billions of years ago, wandering the galaxy ever since? Answering these questions requires more than just observation. It demands a synthesis of data, theory, and imagination. In the grand scheme of cosmic history, 3I Atlas is but a single thread in the vast tapestry of interstellar objects. Yet its fleeting presence serves as a reminder of the universe's boundless diversity and the limits of human knowledge. As we strive to refine our instruments and expand our reach, we must also cultivate a sense of wonder, recognizing that every discovery is a step toward understanding, not a final answer. The ghostly trail of 3I Atlas may fade from view, but its legacy, the questions it inspires, and the mysteries it unveils will endure. As 3I Atlas recedes from Earth's line of sight, its story does not end.
9,
Instead,
8,
it shifts
7,
to a new chapter,
6,
one that
5,
unfolds not from the perspective of
3,
but from
2,
the desolate,
1,
rust-colored plains
0,
of Mars.
and
The
liftoff
planet,
of
long
Space
a
Shuttle
beacon for human
Atlantis on a
curiosity,
mission to
now
build,
stands as an
resupply,
unlikely sentinel
and to
for
do
this
research
interstellar
on the
wonder.
International
By
Space
October
Station.
2025, when 3I
Houston now
Atlas
controlling.
reaches its
Atlantis
closest
begins
approach
its
to the
penultimate
Sun,
journey to
it
shore
will
up the
pass within
International
a
Space
fraction of
Station.
an astronomical unit from Mars, a
Atlantis
distance
now in
that
the proper
transforms the
alignment for its
planet
8.5
into
minute
a
ride to
unique
orbit,
vantage
4.5
point for
million pounds
observation.
of hardware
From
and
this
humans
perch,
taking aim on the
orbiters
International
and rovers
Outpost.
equipped with sensitive cameras and spectrometers may capture glimpses of the comet
30
during its
seconds
most
into the
active
flight,
phase, when its
Atlantis almost 2
nucleus is
miles in
heated to its
altitude,
peak
almost
and
6
its
miles
coma
downrange from the
swells with
Kennedy Space
escaping
Center
gases.
already, traveling
This
500
shift
miles
in
an hour.
perspective is more than a practical necessity. It is a
The 3
symbolic
liquid fuel
leap
main
into the
engines now
future of
throttling back to
interstellar object
72% of rated
research.
performance,
For
going into the
centuries,
bucket, reducing the
humanity
stress
has
on the
studied
shuttle as
the
it breaks through the
cosmos
sound
from a
barrier.
single vantage point, Earth. Yet the universe is vast, and our understanding of it is limited by the confines of our own orbit. Mars, with its thin atmosphere and lack of atmospheric distortion, offers an opportunity to peer into the depths of space with unparalleled clarity. The comet's passage near the planet is a fleeting but profound reminder that the tools of exploration must evolve alongside the questions they seek to answer. If we are to fully comprehend the nature of interstellar visitors, like 3I Atlas, we must look beyond our own world, embracing the challenge of building observatories that ride the winds of other planets and sail the silent seas of interplanetary space. The next segment of this cosmic journey will delve into the specifics of how Mars-based observations might illuminate the secrets of 3I Atlas. It will explore the technological capabilities of existing and proposed missions, the potential discoveries they could yield, and the broader implications for the study of interstellar objects. But for now, let us pause and consider the significance of this moment. As 3I Atlas vanishes from Earth's skies, it leaves behind not an absence but a promise, a testament to the enduring spirit of exploration that drives us to seek out the unknown, no matter how distant or elusive it may seem. In the vast silent expanse of the universe, where stars are born and die inches cycles stretching beyond human comprehension, a lone traveler emerged from the shadows of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS. Stationed at Rio Hurtado, Chile, the object designated 3I Atlas, later renamed Seashell 2025 N1, ATLAS marked itself as a celestial anomaly. It entered the inner solar system at a distance of 4.5 astronomical units (AU) from the Sun, hurtling through the void at a staggering speed of 58 kilometers per second. This velocity, far exceeding the escape velocity of the solar system, confirmed what astronomers had long theorized: 3I Atlas was not bound to our Sun. It was a visitor from another star system, a relic of a distant epoch, carrying secrets etched into its icy heart. As the third interstellar object ever confirmed, following the enigmatic 1I Oumuamua 2017 and the comet-like 2I Borisov 2019, 3I Atlas became a beacon of cosmic curiosity. Its arrival stirred a profound sense of wonder among scientists and stargazers alike, for it represented a tangible connection to the Milky Way's uncharted realms. What ancient stellar nursery birthed this wanderer? How many such travelers had traversed the cosmos unnoticed? And what stories lay hidden within its volatile composition? These questions suspended inches the stillness of space, invited humanity to peer beyond the familiar, to contemplate the infinite tapestry of existence. The comet's trajectory, a hyperbolic arc drawn by gravity's invisible hand, traced a path that would bring it closest to the Sun on 29 October 2025, at a distance of 1.36 AU between the orbits of Earth and Mars. Yet despite its proximity, 3I Atlas would not threaten our world, remaining safely at 1.8 AU from Earth. Instead, it offered a fleeting opportunity to study a fragment of another star system, a frozen time capsule drifting through the vacuum of space. With every observation, every spectral signature captured by Earth's most powerful telescopes, we edged closer to deciphering the mysteries of its origin. But 3I Atlas was not merely a scientific puzzle. It was a reminder of our smallness, a whisper from the cosmos urging us to look outward, to seek understanding inches the dark. The discovery of 3I Atlas began with a faint glimmer inches the southern skies. At apparent magnitude 18, a mere pinprick of light imperceptible to the unaided eye, the object was first spotted by the Atlas telescope as it crossed the galactic plane near the constellations Serpens Cauda and Sagittarius. Initial calculations suggested a highly eccentric orbit, sparking concern that it might pose a threat to Earth. Yet as follow-up observations flooded inches, the picture clarified. Data from the Zwicky Transient Facility (ZTF) and amateur astronomers like Sam Dean revealed a hyperbolic trajectory, its path bending only slightly under the Sun's gravitational pull before it would depart the solar system forever. The comet's speed, a blistering 61 kilometers per second, confirmed its interstellar provenance. Unlike asteroids or comets native to our system, 3I Atlas carried no signature of the Oort cloud or Kuiper belt. It was an exile from elsewhere. What set 3I Atlas apart from its predecessors was its active nature. Unlike 1I Oumuamua, which baffled scientists with its rigid, asteroid-like form, and 2I Borisov, which bore striking similarities to solar system comets, 3I Atlas was a dynamic, evolving entity. As sunlight warmed its nucleus, a core of ice and rock, volatile materials sublimated into gas, forming a glowing coma and a faint tail. The Hubble Space Telescope estimated the nucleus's diameter at less than 1 kilometer, a modest size for an object carrying the weight of interstellar history. Yet even this tiny nucleus held surprises. Spectral analysis by the James Webb Space Telescope unveiled an unusual abundance of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These molecules, forged inches the cold crucibles of interstellar space, hinted at a formation environment distinct from the solar system's icy reserves. Meanwhile, the Very Large Telescope detected cyanide gas and atomic nickel vapor, compounds typically associated with the violent processes of stellar evolution. Together, these signatures painted a portrait of a comet shaped by forces alien to our cosmic neighborhood. The comet's journey through the solar system was a brief but telling chapter inches its ancient story. By October 2025, as it approached perihelion, its solar elongation, the angle between the comet and the Sun from Earth's perspective, narrowed, rendering it invisible to ground-based observers. Yet the Sun's heat would trigger a final burst of activity, releasing jets of gas and dust that might be glimpsed by Mars orbiters. This dual perspective, Earth's loss and Mars' gain, underscored the interconnectedness of planetary observation networks. In tracing 3I Atlas's path, humanity was reminded that even inches the vastness of space, no discovery exists inches isolation. Every data point, every fleeting image, was a thread inches the web of cosmic understanding. To trace 3I Atlas's origins, astronomers turned their gaze to the stars. Its trajectory pointed back to the southern celestial hemisphere, toward the dense starfields of Sagittarius, where the Milky Way's galactic center looms, a region teeming with ancient stars and the remnants of cosmic collisions. Unlike the previous interstellar visitors, which hailed from the solar apex, inches the northern sky, 3I Atlas emerged from a direction long considered unlikely for such discoveries. This southern origin challenged existing models of interstellar object distribution, suggesting either a statistical fluke or the presence of an untapped reservoir of rogue comets inches the galaxy's south. Either way, the comet's path carried implications far beyond its immediate journey. By analyzing its hyperbolic excess velocity, scientists unraveled clues about its galactic provenance, breaking down its motion into radial, transverse, and vertical components revealed a startling fact. 3I Atlas belonged to the Milky Way's thick disk, a stellar population, billions of years older than the Sun. Stars inches this region, formed inches the galaxy's chaotic youth, bear the scars of mergers and collisions, their chemical compositions depleted inches heavier elements. If 3I Atlas shared this heritage, it would be a relic from a time when the Milky Way was still coalescing. Its icy nucleus forged inches the frosty outskirts of a long-vanished protoplanetary disk. Studies by Matthew Hopkins and his team placed the comet's age between 7.6 and 14 billion years, an eon predating the solar system by over 3 billion years. Another analysis, led by Asta Taylor and Darrell Seligman, narrowed the range to 311 billion years. Yet both estimates underscored a singular truth. 3I Atlas was among the oldest objects ever observed, a survivor from the dawn of galactic history. This staggering antiquity raised profound questions. How could a comet endure for such an age without succumbing to the gravitational tides of the galaxy? Why did its volatile compounds persist rather than dissipating into the void? The answers, perhaps, lay inches the comet's vertical velocity, its motion perpendicular to the galactic plane, with a Watts component of 18.5 kilometers per second relative to the Sun. 3I Atlas followed an inclined orbit, oscillating above and below the Milky Way's disk. Such a trajectory shielded it from the dense starfields and gravitational perturbations that might otherwise have torn it apart. It had been a wanderer for eons, a solitary traveler navigating the galaxy's gravitational currents until the Sun's gravity briefly bent its path. In this sense, 3I Atlas was not just a visitor, it was a testament to the resilience of matter, a witness to the slow, inexorable dance of stars and galaxies. Yet its story was not complete. The comet's chemical fingerprint, rich inches carbon dioxide and rare gases, hinted at a formation environment unlike anything inches the solar system. While solar system comets carry water as their primary volatile, 3I Atlas's abundance of CO2 suggested a colder, darker cradle, one where temperatures were low enough for carbon dioxide to condense into ice. Could this reflect conditions inches the host star system's outer reaches? Or perhaps the aftermath of a cataclysmic event, such as a stellar explosion? The presence of cyanide and nickel vapor added another layer of complexity. These molecules, often linked to the late stages of stellar life, implied that 3I Atlas's parent star might have undergone a dramatic transformation, its debris scattering into the void. If so, the comet was not just a relic of planetary formation, but a byproduct of stellar death, a fragment of a star's final act, hurled into interstellar space to drift for eternity. As 3I Atlas vanished from Earth's view, its journey continued. By October 2025, the comet would pass within 0.3 AU of Mars, a mere stone's throw inches cosmic terms. From the red planet's vantage point, it would shine at magnitude 11, a faint but detectable glow for the robotic eyes of orbiters and rovers. Instruments aboard the Perseverance rover or the Mars Reconnaissance Orbiter might capture fleeting images of the comet's coma and tail, offering insights into its structure and activity. This interplanetary observation, a first for an interstellar object, highlighted the growing importance of multiplanetary networks, inches unraveling the universe's mysteries. Yet 3I Atlas's story extended beyond its physical form. Its toxic emissions, cyanide, nickel, and carbon monoxide, sparked unsettling questions. Were these substances unique to its alien origins, or did they mirror the volatile chemistry of our own solar system's early days? Could such compounds, forged inches the crucibles of distant stars, hold clues to the emergence of life? As the comet faded from sight, its legacy endured, a reminder that even the most fleeting encounters with the cosmos can ignite profound inquiries, bridging the gap between the known and the infinite. In the vast, silent expanse of the cosmos, where the laws of physics govern the dance of galaxies and the birth of stars, a solitary traveler arrived inches the summer of 2025, 3I Atlas. A comet born inches the depths of interstellar space, swept into the inner reaches of our solar system, a fleeting guest from a distant corner of the Milky Way, discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, Telescope Inches Chile. This icy wanderer carried with it secrets older than the planets themselves. Its arrival marked a profound moment in human history, the third confirmed interstellar object to cross our cosmic neighborhood, following the enigmatic 1I Oumuamua inches 2017. Yet, unlike its predecessors, 3I Atlas revealed itself not as a stony asteroid or a passive rock, but as an active comet, its nucleus cloaked inches a shimmering coma of gas and dust, illuminated by the sun's distant warmth. This comet's journey began billions of years ago. Long before our solar system coalesced from a swirling nebula, it drifted through the cold void of interstellar space, a relic of a protoplanetary disk that once orbited a dead star. Now, for a brief moment, it became a bridge between worlds, a cosmic messenger, bearing the fingerprints of another stellar nursery. As it hurtled toward perihelion, the point of closest approach to the sun, it traced a hyperbolic path, a trajectory unmistakably foreign to the elliptical orbits of native solar system objects. With a hyperbolic excess velocity of 58 kilometers per second, 3I Atlas moved faster than any natural body bound to the sun, its speed betraying its origins beyond our celestial backyard. To observe this comet was to witness a collision of epoch. The light reflecting off its nucleus and coma traveled millions of miles to reach Earth, carrying with it the faint whispers of a time when the Milky Way's thick disk was young and vibrant. The thick disk, a stellar population older than the Sun, is a region where ancient stars forged inches the early days of the galaxy still linger. If 3I Atlas hails from there, as current models suggest, then it is not merely a visitor, it is a relic of the galactic past, a time capsule from a stellar cradle we can no longer see. Its passage through our solar system offered scientists a rare opportunity to glimpse the chemical and structural diversity of planetary systems beyond our own. and for humanity, a humbling reminder of the universe's boundless complexity. The discovery of 3I Atlas was not a sudden flash of insight, but a gradual accumulation of clues, pieced together by observatories scattered across the globe. On that fateful night, Inches, Chile, the Atlas telescope captured an object moving at 61 kilometers per second, far beyond the velocities typical of solar system comets. At a distance of 4.5 astronomical units from the Sun, it was already deep inches the inner solar system, yet its trajectory hinted at an origin far beyond. Initial calculations suggested a highly eccentric orbit, one that might have brought it dangerously close to Earth. This raised alarms, and the Minor Planet Center (MPC) temporarily listed 3I Atlas on the Near-Earth Object Confirmation page, a precautionary measure to assess any potential threat. But the truth soon emerged. Follow-up observations from the Zwicky Transient Facility (ZTF) and amateur astronomers revealed that 3I Atlas would never come closer than 1.8 astronomical units to Earth, a safe distance that ruled out any risk of impact. Instead, the comet's path was hyperbolic, a shape reserved for interstellar travelers. Further analysis of pre-discovery images, some dating back to late June 2025, confirmed this conclusion. The comet had approached the solar system from the direction of the galactic center, a region choked with stars, which likely obscured its detection until it emerged from the dense stellar fog. The debate over 3I Atlas's nature, whether it was a comet or an asteroid, added another layer of intrigue. Early observations showed no cometary activity, leading some to suspect it might be a rocky body. But by July 2025, telescopes such as the Deep Random Survey X09 and the Canada-France-Hawaii Telescope T14 detected a faint coma and a tail-like elongation, definitive signs of a comet. The coma, a cloud of gas and dust released by the nucleus as it warmed under the sun's rays, was composed of volatile substances like carbon dioxide, water ice, and carbon monoxide. These materials, locked Inches the comet's nucleus for eons, now escaped Inches' delicate plumes, painting a portrait of a world shaped by the frigid conditions of interstellar space. The Hubble Space Telescope provided critical insights into 3I Atlas's physical properties. By analyzing the light scattered by its coma, astronomers estimated the nucleus's diameter to be between 0.32 and 5.6 kilometers, with a most probable size under 1 kilometer. This small size, combined with its rapid motion, underscored the comet's fragile nature, a transient object destined to disintegrate as it neared the Sun. Meanwhile, the James Webb Space Telescope revealed a startling chemical signature. 3I Atlas was unusually rich Inches carbon dioxide, with traces of water vapor and exotic molecules like carbonyl sulfide. Such a composition challenged existing models of cometary evolution, hinting at a formation environment distinct from those of solar system comets. Perhaps the most unsettling discovery came from the Very Large Telescope, VLT, which detected emissions of cyanide gas and atomic nickel vapor. These substances, toxic to earthly life, were present Inches quantities comparable to those observed Inches' native comets. Their presence suggested that the chemical processes governing planetary systems might be universal, that the same ingredients for life and death could be scattered across the galaxy. Yet 3I Atlas's origin Inches the thick disk, a region dominated by ancient stars with metal-poor compositions, raised further questions. How could a comet from such a different stellar nursery mirror the chemistry of our own solar system? Was this a fluke, or a sign that the building blocks of planets are more uniform than previously thought? 3I Atlas's journey through the solar system was a fleeting spectacle, but its implications stretched far beyond the comet's brief visit. As it approached perihelion on 29 October 2025, the sun's radiation would intensify the comet's activity, causing its nucleus to sublimate and release even greater quantities of gas and dust. From Earth, observers equipped with large aperture telescopes tracked its slow brightening, watching as it moved through constellations like Ophiuchus, Scorpius, and Libra. Yet the comet's path placed it Inches an unfavorable position for observation from Earth. By October, it would lie Inches solar conjunction, hidden behind the Sun. Only Mars orbiters positioned at a safer angle might glimpse it at its peak brightness of magnitude 11. This limitation underscored the challenges of studying interstellar objects. Unlike native comets, which can be monitored for decades, interstellar visitors are transient, their trajectories dictated by the gravitational forces of the galaxy rather than the Sun. For 3I Atlas, its closest approach to the Sun, 1.36 astronomical units, was a midpoint inches a journey that would carry it back into the void. By December 2025, it would fade into obscurity, its light dimming as it receded from the solar system. Yet its legacy would endure inches the data it left behind, a record of a world born inches the shadow of a distant star. The origin of 3I Atlas, traced to the thick disk of the Milky Way, opened a portal into the galaxy's ancient history. The thick disk is a stellar population older than the Sun, containing stars formed inches the Milky Way's tumultuous youth. If 3I Atlas hailed from there, it could be over 7 billion years old, nearly twice the age of the solar system. This raised profound questions about the stability of planetary systems inches such an environment. In the thick disk, where stars move inches, chaotic orbits and supernova explosions were more frequent. Could comets like 3I Atlas have survived for eons without being destroyed? Or was it ejected from a young planetary system during a violent episode of gravitational chaos, only to drift inches isolation until its chance encounter with the Sun? The comet's chemical composition added another layer of mystery. While its abundance of carbon dioxide and water ice aligned with the volatile-rich environments of protoplanetary disks, the presence of cyanide and nickel vapor defied easy explanation. These substances, common inches the chemistry of life, were not mere accidents of formation. They were signatures of a process that might link 3I Atlas to the emergence of life itself. Could such toxic compounds, so alien to Earth, play a role inches the biochemistry of other worlds? Or were they simply byproducts of the same cosmic alchemy that forged the planets of our solar system? The study of 3I Atlas also highlighted the limitations of human perception. For much of its journey, the comet remained invisible to all but the most sensitive instruments. Its faintness, masked by the glare of the galactic center, underscored the vastness of the universe and the fragility of our ability to detect its secrets. Yet, the collaboration between professional and amateur astronomers, between cutting-edge telescopes and backyard observers, demonstrated the power of collective curiosity. Every observation, every pixel of data, was a thread inches the tapestry of understanding, weaving together the story of a comet that had traveled across galaxies to reach us. As 3I Atlas faded from view, it left behind more than data. It left a vision of the future. The comet's discovery and study had demonstrated the potential of next-generation telescopes to detect and characterize interstellar objects with unprecedented precision. Instruments like the James Webb Space Telescope and the upcoming Vera-C Rubin Observatory promise to revolutionize our ability to track such visitors, potentially uncovering a menagerie of interstellar bodies with diverse origins and chemistries. With each new discovery, the boundaries of our cosmic knowledge would expand, revealing the interconnectedness of planetary systems across the galaxy. Yet 3I Atlas also posed a challenge: how to prepare for encounters with interstellar objects that might one day pose a threat or offer opportunities for exploration. The comet's harmless trajectory was a reprieve, but future visitors might not share its benign path. Developing technologies to intercept and study such objects, perhaps even to deflect them if necessary, would require international cooperation and a shift inches perspective. No longer could humanity afford to see the cosmos as a distant frontier. It was a dynamic, interactive realm, where our fate was intertwined with that of unseen worlds. And so as the comet's light dimmed inches the Martian skies, it carried with it a message. The universe is not a silent expanse, but a symphony of motion and transformation. In its frozen heart lay the echoes of ancient stars, the building blocks of planets, and the raw materials of life. To study 3I Atlas was to peer into the depths of time and space, to grasp the fragile beauty of existence. Inches a cosmos that is both infinite and intimate. And as we turned our eyes skyward, we knew that the next interstellar visitor would arrive. But who or what it would bring, we could not yet imagine. This script adheres to the requested structure, blending scientific detail with a contemplative tone. Each section explores the discovery, analysis, and implications of 3i Atlas while maintaining a narrative flow that emphasizes cosmic wonder. In the vast, silent expanse of the cosmos, where stars burn for eons and galaxies spiral inches slow, majestic dances, a traveler emerged from the unknown. On 1 July 2025, nestled inches the arid skies of Chile's Rio Hurtado, the Atlas telescope captured a faint smudge against the stellar backdrop, a speck of light that would soon rewrite our understanding of the universe. This was 3i Atlas, the third interstellar object to ever cross the threshold of our solar system. Its arrival was not a mere accident of cosmic drift, but a message etched inches ice and dust, carried by the gravitational tides of the Milky Way as it hurtled toward the Sun at 58 kilometers per second. Faster than any natural body born within our system, 3i Atlas became a beacon of questions. Where had it come from? What secrets lay frozen inches its nucleus? And why did it vanish behind the Sun, cloaked inches solar glare, leaving humanity to ponder its mysteries from afar? The discovery of 3i Atlas was a triumph of modern astronomy, a testament to the vigilance of automated surveys and the collective efforts of scientists and citizen astronomers alike. Yet, its story is far more profound. This comet, older than the solar system itself, is a relic of the galaxy's youth, a fragment of the primordial chaos that birthed stars and planets. To study it is to peer into the distant past, to trace the evolutionary threads of our cosmic neighborhood and beyond. As we follow 3i Atlas's journey, we are reminded that we are not alone. Inches the universe. We are Inches fact, part of a grander narrative, woven together by the same forces that sculpted this interstellar wanderer. By October 2025, 3i Atlas reached the climax of its celestial performance. On 29 October, it would pass closest to the Sun perihelion, at a distance of 1.36 astronomical units, nestled between the orbits of Earth and Mars. Yet, as it approached this moment, the comet's brilliance dimmed from view. The reason? Solar conjunction. For a period spanning nearly a month from 1 October to 9 November, 3i Atlas lingered inches the Sun's shadow, its angular separation from the solar disk shrinking to less than 30 degrees. From Earth, the comet became an invisible ghost. Its light drowned inches the overwhelming glare of our nearest star. Solar conjunction is a cosmic game of hide and seek. When an object's path aligns closely with the Sun from our vantage point, telescopes on Earth cannot safely observe it without risking damage to sensitive instruments. The Sun's corona, a searing halo of plasma, swallows fainter signals, rendering even powerful observatories blind. For 3i Atlas, this meant a critical phase of its journey, the point at which the Sun's heat would most actively sublimate its icy nucleus, remained hidden from direct scrutiny. While ground-based telescopes fell silent, the comet's fate hinged on indirect evidence, models of its trajectory, spectral analyses conducted before and after conjunction, and the hope that space-based missions might catch a glimpse of its fleeting passage. Yet the Sun's role Inches this drama was not merely obstructive, it was the catalyst for 3i Atlas's transformation. As the comet neared perihelion, solar radiation bombarded its nucleus, turning frozen carbon dioxide, water, and methane into gas. These volatile compounds erupted Inches jets, lifting dust into a glowing coma and forming a tenuous tail that stretched millions of kilometers. Though we could not see this spectacle directly, its chemical fingerprints, cyanide, nickel vapor, and carbonyl sulfide, had already been detected by the James Webb and Very Large Telescope. These molecules forged Inches the crucibles of ancient stars, hinted at a history older than our own solar system. 3i Atlas was not just a visitor, it was a time capsule, carrying the echoes of a distant epoch when the Milky Way was young and turbulent. The invisibility of 3i Atlas during solar conjunction underscored a fundamental truth. Our view of the universe is constrained by the tools we wield. Earth-based telescopes, despite their ingenuity, are bound by atmospheric interference, daylight cycles, and the Sun's unrelenting dominance over the sky. To study interstellar objects fully, We must look beyond the limits of our planet. Space-based observatories, like the James Webb Space Telescope, JWST, offer a vantage point untainted by air or gravity. But even they struggle to pierce the sun's veil. Future missions, perhaps dedicated interstellar probes or solar orbiting satellites, may hold the key to unraveling the mysteries of comets, like 3I Atlas. Consider the implications of this limitation. If 3I Atlas had not emitted detectable gases before conjunction, we might have lost all trace of its chemical composition. Similarly, if its trajectory had placed it closer to the sun, the intense radiation could have stripped its coma entirely, leaving nothing but a barren nucleus to escape into deep space. Such scenarios highlight the fragility of observation and the serendipity required to intercept interstellar visitors. Every discovery is a stroke of luck, alignment of timing and technology that allows us to glimpse the infinite. But solar conjunction also serves as a metaphor for the broader human condition. Just as 3I Atlas disappeared into the sun's embrace, so too do many truths elude us, obscured by gaps, inches knowledge, or the sheer scale of the cosmos. The comet's journey mirrors our own, a brief luminous arc against the void, followed by a retreat into obscurity. Yet even inches its absence, 3I Atlas left indelible marks. Its hyperbolic orbit, traced with mathematical precision, revealed that it hailed from the Milky Way's thick disk, a region of ancient stars where the galaxy's earliest generations once thrived. Its age, estimated at 7 to 14 billion years, positioned it as a relic of the cosmic dawn, predating the formation of Earth and the oceans. In studying this object, we are not merely observing a comet, we are deciphering a message from the past. Encoded inches ice and gas. As 3I Atlas receded from the sun and re-emerged into view inches, late 2025, its light grew fainter, its tail dissolving into the cold vacuum of space. Yet its legacy endures, not just inches data tables and spectral graphs, but inches the questions it ignited. Why does the galaxy hurl such ancient comets into our laps? How many more interstellar travelers lurk inches the dark, waiting to be found? And what can they teach us about the origins of life, the evolution of stars, and the destiny of worlds? The story of 3I Atlas is a reminder that we are stardust ourselves, born from the remnants of exploded suns and scattered across the cosmos by time and gravity. Our telescopes are extensions of our curiosity, reaching outward to touch the fabric of reality. Yet, for all our technological prowess, we remain humbled by the vastness of what we cannot yet comprehend. The next interstellar visitor may arrive inches a century, a millennium, or never at all. But when it does, we will be watching, eager to listen to the whispers of the universe. In the end, 3I Atlas is more than a comet. It is a mirror, reflecting our place inches the cosmic order. Amper's transient spark inches the night sky. It reminds us that the universe is alive with motion, mystery, and the endless unfolding of stories older than memory. As we turn our eyes to the stars, we are not mere observers. We are participants inches a dance that has no beginning and no end. Written inches the language of light and time. In the vast, uncharted expanse of the Milky Way, where the fabric of space-time stretches thin and the echoes of ancient stars hum through the void, a solitary traveler has emerged. 3I Atlas, an interstellar comet born inches the shadowed depths of the galaxy's thick disk, hurtles through the solar system like a whisper from a forgotten epoch. Its arrival is not merely an astronomical event, but a profound encounter with antiquity. A fleeting moment when the universe itself chooses to unveil one of its oldest secrets. For over 7 billion years, this icy relic has drifted through the cosmic wilderness, untethered by the gravitational pull of any planetary system, until its path intersected with our own. Now, as it glides past the sun inches the autumn of 2025, 3I Atlas offers humanity a rare glimpse into the primordial stew from which galaxies, stars, and life itself coalesced. To observe this comet is to peer into a mirror held up by the cosmos, reflecting a time when the Milky Way was young and the building blocks of worlds were still scattered like stardust across the dark. What makes 3I Atlas extraordinary is not just its origin, but the story it carries. Unlike the transient visitors One-Eye Oumuamua and Two-Eye Borisov, which arrived as enigmatic wanderers from the galactic field, Three-Eye Atlas hails from a far older and more mysterious region, the thick disk of the Milky Way. This is a realm where stars, forged inches the early days of the galaxy's formation, burn slowly and silently, their atmospheres laced with the signatures of an ancient chemical heritage. Here, the interplay of gravity and time has shaped a population of objects unlike any found inches our own backyard. Three-Eye Atlas is not just a comet, it is a time capsule. It is a time capsule, its nucleus preserving volatile compounds and organic molecules that may hold clues to the conditions that birthed the first planetary systems. As it dances through the inner solar system, its coma, a fragile shroud of gas and dust, unfurls like a veil of memory, revealing the fingerprints of a bygone era. In this quiet ballet of ice and sunlight, the universe whispers truths that transcend the boundaries of human understanding, reminding us that we are but ephemeral observers, inches a story far older than ourselves. To comprehend the significance of Three-Eye Atlas, one must first decode the celestial passport embedded inches its trajectory. Discovered on 1 July 2025 by the Atlas Telescope's Inches Chile, this comet entered the inner solar system at a staggering heliocentric distance of 4.5 astronomical units, AU, traveling at a hyperbolic excess velocity of 58 kilometers per second. This speed alone betrays its extraterrestrial origin. Unlike comets bound to the sun's gravitational embrace, Three-Eye Atlas follows a hyperbolic path, an open-ended trajectory that ensures it will escape the solar system after its brief passage. Such trajectories are rare, reserved for objects whose velocities exceed the escape velocity required to break free from the sun's gravitational well. For Three-Eye Atlas, this velocity was not acquired within our system, but inherited from its birthplace, a testament to the dynamic processes that govern the Milky Way. The comet's motion traces back to the heart of the galaxy's thick disk, a region where stellar populations are ancient, their orbits tilted and elongated, compared to the orderly plane of the thin disk where our solar system resides. The thick disk is a relic of the Milky Way's violent youth, a time when mergers and collisions between proto-galaxies stirred the cosmos into chaos. Stars born inches this era are metal poor, their atmospheres bearing the scars of a universe still inches its infancy. By analyzing the velocity components of Three-Eye Atlas, its radial, transverse volts, and vertical Watts motions, astronomers have determined that the comet's path is inclined at a steep angle relative to the galactic plane. This tilt places it among the thick disk's denizens, a population that includes some of the oldest stars inches the galaxy. Yet the comet's journey is not merely a product of galactic dynamics. Its composition tells another tale, one written inches the chemistry of its nucleus and coma. Observations by the James Webb Space Telescope, JWST, have revealed that Three-Eye Atlas is unusually rich inches carbon dioxide, with traces of water ice, carbon monoxide, and carbonyl sulfide. These volatile compounds, preserved inches a frozen state for eons, suggest that the comet formed inches a cold, distant region of its home system, far beyond the frost line, where water and other volatiles could condense into ice. The presence of cyanide gas and atomic nickel vapor, detected by the Very Large Telescope, further hints at complex chemical processes that may have occurred during its formation or subsequent interactions with stellar radiation. Perhaps most astonishing is the comet's estimated age. Studies by Matthew Hopkins and colleagues, published Inches Nature Astronomy Inches July 2025, suggest that Three-Eye Atlas is between 7.6 and 14 billion years old, far older than the solar system's 4.6 billion year history. This places its origin inches an era when the Milky Way was assembling itself from smaller, gas-rich proto-galaxies. If accurate, Three-Eye Atlas predates the formation of our Sun and the planets, surviving the cataclysmic events that shaped the galaxy. Its survival is nothing short of miraculous. Over billions of years, the gravitational tides of passing stars and molecular clouds could have shattered it or hurled it into the abyss. Yet here it is, a silent witness to the dawn of the cosmos, now passing through our neighborhood as if to remind us of the universe's boundless patience and resilience. The study of 3I Atlas forces us to confront the limitations of our cosmic perspective. For centuries, humanity has peered into the heavens with the assumption that the solar system is a self-contained laboratory, a microcosm of universal processes. But 3I Atlas disrupts this notion, revealing that our corner of the galaxy is but a single note, inches a symphony of interstellar exchange. The comet's journey through the thick disk underscores the interconnectedness of stellar systems, a reality where material is not confined to individual star systems but flows freely across the galactic scale. Just as rivers carve landscapes over millennia, the gravitational interactions between stars and their planetary systems sculpt the distribution of comets and asteroids, scattering fragments like seeds carried by the wind. This realization has profound implications for our understanding of planetary formation. The thick disk, with its ancient metal-poor stars, represents a different chemical environment from the thin disk, where our solar system resides. The metals elements heavier than helium that define the composition of planets, and their moons are forged inches the hearts of massive stars and dispersed through supernova explosions. In the thick disk, where star formation began earlier and proceeded more slowly, these heavy elements were less abundant. Comets like 3I Atlas, formed inches such an environment, may carry pristine samples of primordial material that predate the galactic enrichment cycle. By studying their chemistry, scientists can reconstruct the conditions under which the first planetary systems assembled, shedding light on the universality or uniqueness of Earth-like worlds. Moreover, 3I Atlas challenges the prevailing models of interstellar object origins. Prior to its discovery, astronomers had predicted that most interstellar visitors would originate from the solar apex, the direction inches which the sun is moving through the galaxy. This assumption was rooted in the idea that the gravitational slingshots of passing stars would preferentially eject objects inches the direction of the sun's motion. However, 3I Atlas's southern origin defies this expectation, suggesting that the galactic distribution of interstellar objects is more complex than previously thought. Are such southern origin comets rare anomalies, or do they represent a hidden majority? The answer lies in the data, but for now, 3I Atlas serves as a reminder that the universe often reveals its secrets in ways we least expect. On a deeper level, the comet's existence compels us to reconsider our place in the cosmos. When we gaze at the night sky, we see stars as distant, static pinpricks of light. But 3I Atlas reminds us that the galaxy is a living, breathing entity. Its components inches constant motion, the atoms inches our bodies, the oxygen we breathe, and the calcium inches our bones were once part of stars that lived and died long before the solar system existed. In this sense, 3I Atlas is not just a visitor from another star system, it is a kinship link, a tangible connection to the cosmic family tree that binds all matter together. The study of interstellar objects like 3I Atlas is still in its infancy, but it has already begun to reshape our understanding of the universe. Future missions, such as the European Space Agency's Lagrange mission or NASA's proposed Interstellar probe, aim to intercept and analyze such objects in greater detail. These efforts will not only refine our knowledge of interstellar comets, but also provide insights into the structure and evolution of the Milky Way. For now, however, 3I Atlas remains a singular marvel, a fleeting beacon that pierces the veil of time and space. Its passage through the solar system is a humbling reminder that we are not the center of the universe, but rather a small transient part of its grand design. As 3I Atlas fades from view, its legacy endures, not as a mere footnote in the annals of astronomy, but as a catalyst for a new era of exploration. Its journey through the inner solar system has opened a door to questions that transcend the boundaries of individual disciplines, weaving together astrophysics, planetary science, and even philosophy. What other interstellar travelers await discovery? Their paths yet to be charted. How many more comets like 3I Atlas lie dormant in the galactic wilderness? Their stories waiting to be told. And what might these cosmic messengers reveal about the origins of life, the diversity of planetary systems, or the ultimate fate of the Milky Way? The answers to these questions will require more than advanced telescopes and spacecraft. They demand a shift inches perspective. To study 3i Atlas is to embrace the humility of the unknown, to recognize that every observation is a step toward a deeper understanding of the universe and of ourselves. As we turn our eyes to the stars, we are reminded that the cosmos is not a silent void, but a dynamic, ever-changing tapestry. In this tapestry, each thread, be it a star, a comet, or a grain of stardust, plays a role inches the grand narrative of existence. And as we continue to unravel this story, we find not just knowledge, but a profound sense of wonder, the realization that we are part of something far greater, a journey that began long before us and will endure long after. In the next segment, we will delve into the technological innovations that have enabled humanity to detect and study interstellar objects, like 3i Atlas. From the cutting-edge instruments of ground-based observatories to the revolutionary capabilities of space telescopes, these tools have transformed our ability to probe the distant reaches of the cosmos. Alongside this, we will explore the challenges and triumphs of international collaboration in astronomy, a field where the pursuit of knowledge knows no borders. As we embark on this next chapter, let us carry forward the spirit of curiosity and awe inspired by 3i Atlas, for it is this spirit that will guide us toward the next great discovery.